Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, the universe speaks softly, and even the largest ideas are invited to slow down for the evening. Tonight, we are going to spend some time with something so enormous that it almost resists description. Not because it is hidden, not because it is fictional, and not because scientists are unsure whether it exists, but because the human mind was never really built to feel comfortable with distances this large. Our gentle subject tonight is known as the Boss Great Wall, a colossal arrangement of galaxies stretching across the observable universe on a scale so vast that even astronomers occasionally pause, stare at the numbers, and quietly reconsider their life choices. It is called a wall, though no bricks were involved, no mortar, no scaffolding, no cosmic construction crew in reflective jackets. Instead, it is a grand clustering of galaxies, groups of galaxies, and filaments of matter spread across space in a pattern so large that language starts to wobble a little when trying to explain it. And perhaps that is part of the charm. Some things are not difficult because they are complicated. Some things are difficult because they are simply too big. Before we begin, I'd love to know where in the world you're listening from tonight and what time it is in your corner of Earth right now. Perhaps it is late evening. Perhaps dawn is just beginning. Perhaps you're somewhere between one task and the next, looking for a quieter kind of company. Wherever you are, I'm glad you're here. If you find this little voyage soothing, interesting, or simply a pleasant place to let your thoughts rest for a while, I'd be grateful if you gave the video a like, maybe subscribed, and joined us again for future wanderings through science, space, history, and all the strange things reality keeps tucked away. Now, settle in. Loosen the day from your shoulders. Let your breathing slow to a pace that suits you, because tonight we begin with a wall so large that even calling it a wall may be underselling the matter entirely. When most of us hear the word wall, we imagine something familiar. A garden wall, a castle wall, a wall between rooms, something solid, useful, politely vertical, and measured in meters rather than millions of light years. A wall is usually built to separate one place from another. The boss. Great Wall does none of these things. You cannot stand beside it. You cannot lean on it. You cannot walk around it complaining about parking. It does not divide territories. It does not block winds. It does not keep out invaders unless those invaders happen to be moving through intergalactic space and are extremely patient. Instead, this wall is a name we gave to a pattern. That may sound underwhelming at first, but patterns are often where the deepest truths hide. Consider constellations. Orion is not a man with a belt and a sword. It is a pattern of stars seen from our viewpoint. The Big Dipper is not kitchen equipment suspended in darkness. It is arrangement and perspective. Human beings are remarkably talented at taking scattered things and finding shapes in them. Sometimes those shapes are useful. The Boss Great Wall is one of those cases. Across the universe, galaxies are not sprinkled evenly like sugar on a tabletop. They gather, they cluster, they stretch into strands, knots, sheets, and vast connected regions separated by enormous empty spaces. If you could step far enough back, the universe would not look like random dust. It would look more like foam, webbing, or the branching structure of something alive. That comparison is only visual, of course. The universe is not secretly a sponge, though science has surprised us before. Within that cosmic web, astronomers discovered one especially immense structure using data from a survey called BOSS, short for the Baryon Oscillation Spectroscopic Survey. It was a project dedicated to mapping galaxies and measuring the large-scale structure of the cosmos with great care and excellent patience. Those two qualities, care and patience, are responsible for many of humanity's best discoveries. The survey examined the positions of galaxies spread across huge volumes of space. When researchers analysed the data, they identified a massive connected complex made of galaxy superclusters and filaments. This structure was so large that it earned a dramatic name, the boss Great Wall. And to be fair, if you discover something spanning more than 1 billion light-years, subtle branding may no longer be necessary. To appreciate the scale, it helps to start smaller. Earth is about 12,742 kilometers across, already respectable. The distance from Earth to the Moon is about 384,000 kilometers, much farther, yet still close enough in cosmic terms that light reaches it in roughly 1.25 seconds. The Sun is around 150 million kilometers away. Light takes about 8 minutes to arrive. If the Sun politely vanished, we would continue about our business for 8 minutes before realizing the schedule had changed. Our solar system, depending on how generously you define its outer limits, extends vastly farther. Then comes the nearest stars, then the Milky Way galaxy, containing hundreds of billions of stars, then neighbouring galaxies, then galaxy groups, then clusters, then superclusters. And somewhere far beyond the scales where everyday intuition resigned and went home, we encounter structures like the Boss Great Wall. It stretches for over 1 billion light-years, in some measurements and descriptions, around 1 billion light-years in extent, composed of multiple connected superclusters. Numbers vary slightly depending on method and boundaries, which is common in astronomy. The universe does not always provide crisp edges and convenient labels. If that number feels hard to imagine, that is because it is. A light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. Light can circle Earth more than 7 times in a single second. It is fast enough to make most human transport options look reflective and embarrassed. Now let that speed continue for a year, then multiply it by 1 billion. And that is the sort of scale we are discussing tonight. There is a calming honesty in admitting when something exceeds intuition. We do not need to pretend otherwise. The mind was designed to track footsteps, seasons, faces, fruit trees, weather, and perhaps whether something with teeth was nearby. It was not optimized to emotionally process billion light-year geometry. Yet here we are trying anyway, which says something lovely about our species. We keep reaching. Now, an important detail. The boss. Great Wall is not a single object forged in one place like a planet or star. It is a large-scale arrangement of many smaller structures linked by gravity and cosmic history. Imagine cities, roads, regions, and continents forming patterns on a map. No one poured them from a mould. They emerged through countless processes over time. Likewise, galaxies formed, matter clumped, gravity amplified tiny differences, and over billions of years the universe developed texture. That word matters here. Texture. We often speak of space as empty, smooth, and silent. But on the grandest scales, space has texture. Density varies. Matter gathers in strands. Voids open like enormous cosmic basins where relatively few galaxies dwell. Between these voids run filaments rich with galaxies and dark matter, intersecting in dense nodes where clusters grow. The Boss Great Wall is part of that textured reality. And naturally, once scientists found it, another question followed. Should something this large exist at all? That question carries us gently into one of the most interesting tensions in cosmology. There is a guiding assumption called the cosmological principle. In simple terms, when viewed on large enough scales, the universe should look roughly homogeneous and isotropic. That means matter should be distributed fairly evenly overall, without preferred directions or giant irregularities dominating everything. Not perfectly smooth in small regions, of course. Galaxies, stars, planets, and your kitchen drawer all demonstrate local disorder, but zoom out far enough, and the universe is expected to average out. Structures like the Boss Great Wall make scientists examine what far enough really means. If immense walls, filaments, and clusters persist on scales larger than expected, then either our statistical expectations need refinement, our definitions need care, or the universe is more structured than some simplified assumptions suggest. Fortunately, science enjoys this sort of discomfort. It is how progress happens. When observations disagree with tidy expectations, researchers do not usually faint onto chaise lounges. They gather more data, revise models, argue politely in papers, and occasionally name things with flair. The Boss Great Wall does not necessarily break cosmology, but it does ask questions loudly enough to be noticed. That alone makes it worth our attention. There is also something wonderfully human in our reaction to such discoveries. We hear of a giant wall in space and immediately want to compare it to things we know. How many Milky Ways across is it? Far too many for conversation. Could we travel along it? Not in any practical sense unless you are immortal, very committed, and own a remarkable vehicle. Could we see it from Earth? Not with the naked eye as a wall shape. We infer it through surveys, redshifts, mapping, and careful reconstruction. Much of modern astronomy involves learning to see through data rather than eyesight alone. That may sound less romantic than stargazing, but it is its own kind of wonder. We built tools that let us detect patterns across billions of light years using light that began travelling before Earth had modern humans. That is an extraordinary sentence to be able to say at all. And yet, amid these scales, your own evening continues quietly. Perhaps there is a lamp nearby. Perhaps a blanket. Perhaps the faint sound of traffic outside or rain on a window. While we speak of colossal cosmic architecture, your life is happening on a much smaller stage of tea mugs, floorboards, breathing, and ordinary time. Both scales are real. That contrast is one reason astronomy can feel soothing. It reminds us that small does not mean unimportant, and large does not mean urgent. The Boss Great Wall has existed without requiring your attention for ages. It can wait a little longer while you get comfortable. Step a little farther with me now, because once a name like the Boss Great Wall enters the room, it naturally invites a certain kind of misunderstanding. The phrase sounds dramatic, it sounds solid. It sounds like something you might crash a spaceship into if your navigation system were distracted. It suggests a towering barrier stretching through darkness like a cosmic version of ancient stone fortifications, perhaps complete with battlements, stern guards, and a sign saying visitors must remain in designated lanes. In truth, it is stranger than that and far more interesting. The Boss Great Wall is not a wall in the everyday sense. It has no surface, no thickness you could stand upon, no front side, no back side, no official entrance. It does not block movement. Light passes through it. Galaxies within it continue their own motions. Space itself does not suddenly become crowded with cosmic masonry. Instead, it is what astronomers call a large-scale structure, a vast arrangement of galaxies, galaxy clusters, superclusters, and connecting filaments that together form a coherent pattern across an astonishing distance. That may sound technical, so let us slow it down. Imagine looking at a city from high above at night. You would see streets, neighbourhoods, dense bright centres, quieter edges, and long ribbons of lights connecting one region to another. If you zoomed out even farther, patterns would emerge that are invisible from street level. Roads feed into highways, districts cluster near rivers, suburbs wrap around cores. None of that structure is obvious to a person standing beside a bakery, wondering whether it is still open. Perspective changes everything. The Boss Great Wall is a bit like that. On the scale of individual galaxies, you're looking at separate islands of stars, each containing billions of suns. But when astronomers zoom out and map many thousands of galaxies across immense volumes of space, those islands begin to reveal a larger design. They are not evenly scattered. They gather into filaments, nodes, sheets, and clusters. Between them lie enormous voids, regions where relatively few galaxies reside. Over cosmic distances, the universe resembles a network more than a random spray. Some compare it to soap bubbles, foam, roots, or neurons. These are only visual analogies, of course. The universe is not secretly thinking thoughts through galaxies, though it does occasionally look suspiciously organised. Within that network, the Boss Great Wall is one of the most striking known examples of connected large-scale structure. Its name comes from the Baryon Oscillation Spectroscopic Survey, commonly shortened to BOSS. That survey was part of the Sloan Digital Sky Survey family of projects, one of the most ambitious astronomical mapping efforts ever undertaken. Using powerful telescopes and spectroscopic instruments, astronomers gathered data on the positions and distances of huge numbers of galaxies. Then came the patient part. Once you have a great many galaxies plotted in 3 dimensions, you can begin looking for patterns. Not imagined patterns, not casual guesses, but statistically meaningful concentrations and connected systems that stand out from the broader cosmic distribution. That is how the BOSS Great Wall was identified. Researchers analysing the data found a massive complex made up of several large superclusters linked together. These included dense regions of galaxy concentrations and elongated structures bridging them. Collectively, they formed something so extensive that it deserved special notice. And, being scientists who occasionally allow themselves a memorable title, they called it the BOSS Great Wall. Now, to understand why this matters, we need to clarify what is being connected. A galaxy is a gravitationally bound system of stars, gas, dust, dark matter, and often a supermassive black hole at its centre. The Milky Way is one such galaxy. A galaxy cluster is a group of many galaxies bound together by gravity. A supercluster is a still larger grouping of galaxy clusters and associations spanning huge distances. Beyond that, things become less neatly bound and more structurally descriptive. Matter arranges into filaments and walls that may not behave like one single object, but still form recognizable large-scale features. So the BOSS Great Wall is not one item. It is a grand assembly. That distinction is important. When we hear of a mountain, we imagine one mountain. When we hear of a planet, we think of one sphere. But when we hear of the BOSS Great Wall, we're hearing about many systems participating in one larger pattern. It is more like a continent than a boulder. Even that comparison is imperfect, but it helps. Its estimated scale is around 1 billion light-years across, depending on how boundaries are drawn and which dimensions are emphasized. Astronomical structures rarely come with crisp edges or convenient fences. Nature prefers gradients, overlaps, and politely vague margins. If you ask where the wall begins, the universe may respond with silence. If you ask where it ends, it may offer another billion light-years of ambiguity. That does not make it less real. It simply means reality is under no obligation to behave like textbook diagrams. Now let us pause with that number. 1 billion light-years. Light moves at roughly 300,000 kilometers per second. It circles Earth several times in 1 second. It reaches the moon in a little over a second. It reaches the sun in about 8 minutes. Yet to cross 1 billion light-years, light itself would need 1 billion years. By the time light travelled from one side of such a structure to the other, continents on Earth would drift, species would appear and vanish, mountains would rise and erode, oceans would change shape, and human history as we know it would be too brief to register as more than a flicker. That is the scale hidden inside the name. And still, despite that size, it is made of emptiness as much as matter. This is another delightful surprise of astronomy. Enormous structures sound dense and crowded. In practice, galaxies are separated by immense distances. Even within clusters, there is far more space than substance. If you travelled through the BOSS Great Wall, most of your journey would involve crossing vast stretches of darkness, punctuated by islands of stars. So it is a wall only statistically. That phrase deserves appreciation. It means the density of galaxies in that region is significantly higher and more connected than average across those scales. It means when you map enough data, a structure emerges that is not random noise. It means pattern rises above background. And human beings have become surprisingly good at noticing that. There is something almost tender about the process. Tiny creatures on one planet built instruments, learned spectroscopy, developed mathematics, catalogued light from galaxies unimaginably distant, and then recognized that those galaxies together formed one of the largest structures known. No individual person can see the Boss Great Wall with their eyes. No one can float outside the universe with a clipboard and admire it directly. We know it through inference, collaboration, and patience. That may be the most human way to know anything important. Naturally, once something this large is found, people ask whether it should exist at all. That question emerges because of a guiding concept in cosmology, known as large-scale homogeneity. In broad terms, if you average matter over sufficiently huge scales, the universe should appear fairly uniform. There can be local clumps and voids, certainly, but beyond some size threshold, those irregularities are expected to smooth out. Structures like the Boss Great Wall test our understanding of where that smoothing scale lies. If enormous connected features keep appearing, then cosmologists must ask careful questions. Are these structures rare but expected outcomes of normal cosmic evolution? Are they partly artifacts of how we define connected regions? Are we selecting dramatic examples from a larger statistical distribution? Do our models need refinement? Science advances by such questions, not by pretending to have none. The Boss Great Wall does not necessarily overturn modern cosmology. It does, however, provide a valuable challenge. It asks our theories to explain real data rather than idealize simplicity. That is useful. The universe tends to be an excellent critic. There is also the matter of time. When we observe distant galaxies, we are seeing old light. The farther away something is, the longer its light has travelled. So the Boss Great Wall is not just a structure in space, it is also a structure in time. We observe it as it was long ago, when that light began its journey toward us. Astronomy often works this way. To look outward is to look backward. That means maps of cosmic structure are also records of cosmic history. We do not merely locate galaxies, we glimpse earlier eras of the universe, and perhaps that helps explain why such topics can feel calming at night. They quietly rearrange urgency. Whatever happened in your inbox today, it exists beside a universe where light travels for billions of years carrying news of ancient galaxies. Whatever awkward thing you said last Tuesday now shares reality with structures so large that language struggles to frame them. Perspective does not erase problems, but it can soften their sharpest edges. Now, another subtle point. The Boss Great Wall is not permanent in the everyday sense. Cosmic expansion continues. Galaxies move. Gravity reshapes regions. Over immense timescales, structures evolve. The wall is not a frozen monument, but part of an ongoing universe. Everything changes, even the grandest patterns. That includes us, though usually on more practical schedules involving sleep and breakfast. If you're imagining the Boss Great Wall now, do not worry if the picture remains fuzzy. That is normal. Some realities cannot be pictured cleanly because they were never meant for ordinary intuition. Instead of forcing an image, hold a simpler understanding. Across the universe, galaxies gather into networks. Within that network, one particularly vast connected region was identified through careful surveys. We gave it a memorable name, and by naming it, we made one more impossible scale slightly easier to talk about. Soon, another question naturally arrives. If no one can step back and directly see such a thing, how exactly did astronomers find it? How do you discover a wall made of galaxies spread across billions of light years? At first glance, discovering something like the Boss Great Wall sounds almost impossible. Finding a chair in a dark room can be challenging enough, especially if you're moving barefoot and full of misplaced confidence. Finding your keys can consume an afternoon. Finding one missing sock has defeated civilizations. So how exactly do astronomers locate a structure stretching across roughly 1 billion light years when they cannot step outside the universe, cannot take a panoramic photograph of everything, and cannot simply ask the galaxies to stand in a neat line for inspection? The answer is both elegant and deeply human. We map, we measure, we gather tiny signals patiently over many years, then allow patterns to emerge. That is the quiet secret behind many grand discoveries. They often begin not with thunder, but with careful bookkeeping. To understand how something this large is found, it helps to begin with a simple truth. The night sky, beautiful as it is, can be misleading. When you look upward, stars appear scattered across a flat dome. Constellations seem close together. Bright points look like neighbours. Yet many stars that appear side by side are separated by enormous distances. Some are nearby, others are far beyond them. The sky is not a painting. It is depth disguised as surface. Galaxies present the same challenge on a far larger scale. If you photograph the heavens, you may capture countless galaxies as tiny smudges or points of light. But a flat image alone does not tell you where those galaxies sit in three-dimensional space. One galaxy may be relatively close. Another, appearing beside it, may be billions of light years farther away. So the first challenge in finding giant cosmic structures is this. You must turn the sky from a flat image into a three-dimensional map. That sounds straightforward until one remembers the objects involved are unimaginably distant, faint, numerous, and not inclined to label themselves. Still, astronomers are persistent creatures. The process begins with sky surveys. These are systematic efforts to observe huge portions of the sky using telescopes equipped with sensitive cameras and instruments. Rather than studying one star or one galaxy at a time, surveys aim for scale. They collect data on thousands, then millions of objects. One of the most influential examples is the Sloan Digital Sky Survey, often called SDSS. It has spent years mapping the cosmos in extraordinary detail. The BOSS project, the Baryon Oscillation Spectroscopic Survey, was one branch of that larger effort. And yes, astronomy does occasionally produce names that sound like either prestigious institutions or people who expect updates by Monday morning. BOSS had a serious purpose. It was designed to study the large-scale distribution of galaxies and help measure the expansion history of the universe. To do that, astronomers needed more than photographs. They needed distances, and distance in astronomy is often determined through light. Now, light does many useful things. It illuminates rooms, warms planets, reveals stars, and occasionally exposes that one shelf you forgot to dust. But for astronomers, light is also information. When light leaves a distant galaxy and travels across expanding space toward Earth, its wavelength changes. As the universe expands, the light is stretched. This shifts it toward the red end of the spectrum, a phenomenon known as redshift. Redshift is one of the most important tools in cosmology. The greater the redshift, generally speaking, the farther away the galaxy is, and the longer its light has travelled. So by measuring the spectrum of a galaxy's light, astronomers can estimate its distance. That is where spectroscopy enters the story. A spectroscope breaks incoming light into its component wavelengths, much like a prism spreading sunlight into colours. Within that spread of light are distinctive signatures from elements such as hydrogen, oxygen, and others. These spectral lines appear at known wavelengths. If those lines are shifted toward red, astronomers can calculate how much stretching occurred. That shift becomes a clue to distance. Imagine hearing a familiar song played slower and deeper than usual. You would know it had changed in transit. Astronomers do something similar with light. And once you measure enough galaxies this way, something remarkable happens. You no longer have just points on a sky chart. You have coordinates in depth. You can begin placing galaxies into a three-dimensional cosmic map. This is where giant structures stop seeming impossible to find. Suppose you map a few dozen galaxies. Not enough information, map a few hundred. Better, but patchy. Map hundreds of thousands across immense volumes of space, and patterns start to reveal themselves. Clusters appear. Filaments stretch between dense regions. Voids open like giant empty basins. Sheets and walls emerge from what once looked like scattered noise. The Boss Great Wall was found through precisely this kind of large-scale mapping. Researchers examined the positions of many galaxies in survey data and identified connected superclusters and dense regions forming one immense complex. It was not discovered because someone noticed a suspiciously wall-shaped object through a telescope eyepiece late one evening. It was discovered because data, once assembled, began telling a story. That distinction matters. Modern astronomy is often less about seeing and more about reconstructing. No person directly looks at the Boss Great Wall the way one looks at a mountain range from an airplane window. Instead, scientists combine observations, measurements, models, and statistical tools until the structure becomes evident. This may feel less romantic than old-fashioned stargazing, but I would argue it has its own beauty. A species on one small planet learned how to detect patterns across billions of light years, using light older than human civilization. That is romance of a very high order. Now, let us slow down and picture what astronomers are really doing. Imagine you are standing in a foggy valley at night with scattered lanterns glowing in the mist. You cannot see the full landscape, you only see points of light. Some are near, some are far. If you could measure the brightness, colour and subtle shifts of each lantern, then plot their positions carefully, you might eventually infer roads, villages, ridges, and valleys hidden in darkness. That is not the universe, of course, but it is close enough to feel the method. Astronomers infer unseen structure from distributed light. There is another complication, however. The universe is large enough to be inconvenient. No single observation captures everything. Surveys take years, instruments must be calibrated, data must be cleaned, false signals removed, selection effects understood, gaps accounted for, computers enlisted. Some nights weather interferes, some objects are too faint, some measurements need checking. Somewhere, always, a spreadsheet waits patiently. Science can be glamorous in documentaries. In practice, it often involves persistence and coffee. Once data is collected, researchers use algorithms and statistical methods to identify meaningful structures. This is necessary because boundaries in the cosmos are rarely obvious. Where does a cluster end? Where does a filament begin? At what density does a region qualify as part of a wall? These are not silly questions. They are central questions. Nature does not draw lines around structures and attach neat labels. Humans do that afterward for convenience. So when scientists identified the Boss Great Wall, they were recognizing a physically meaningful arrangement in galaxy distribution, not uncovering a pre-labeled monument. It is a bit like defining a mountain range. Peaks, valleys, foothills, and ridges blend together. Yet we still meaningfully describe ranges because patterns are real even when edges are fuzzy. The same applies here. Now perhaps you're wondering whether dark matter plays a role. Very much so. Most matter in the universe is not ordinary visible matter. Dark matter, whatever its exact nature, exerts gravity and helps shape cosmic structure. Galaxies tend to form within larger dark matter halos, and along dark matter scaffolding established over cosmic time. So when astronomers map visible galaxies, they are also indirectly tracing a deeper gravitational framework. The luminous galaxies are like lights strung along an unseen architecture. That hidden architecture helped create structures like the Boss Great Wall. There is something quietly satisfying in that image. We see only part of reality, yet even that part can guide us toward the rest. Another challenge in finding giant structures is time itself. When we observe distant galaxies, we see them as they were when their light began travelling toward us. Some of the galaxies used in these maps are seen hundreds of millions or billions of years in the past. So cosmic mapping is not like surveying a static landscape. It is more like assembling a vast historical atlas where different regions are observed at different eras. and yet the mathematics of cosmology allows us to make sense of it. This is one reason astronomy can feel so humbling. It asks us to think not only across distance, but across time layered into distance. A nearby galaxy may appear more recent than a farther one. Looking deeper into space means looking deeper into history. To build one, map. Scientists are partly building a timeline. Now let us address a subtle but important point. Could giant structures simply be illusions caused by chance clustering? Sometimes random distributions can create apparent patterns. Humans are especially talented at spotting faces in clouds and significance in toast. Scientists know this, which is why they test patterns statistically. When the Boss Great Wall was identified, researchers compared observed distributions against expectations from cosmological models and random arrangements. They assessed whether the connected structure was notable beyond chance. This discipline matters. Science does not trust first impressions, and wisely so. It asks for evidence twice, sometimes 3 times. So how do you even find something that big? Not by seeing the whole thing directly, not by travelling there, not by luck. You find it by collecting the light of countless galaxies, measuring their redshifts, plotting their positions, comparing patterns, checking assumptions, refining methods, and letting structure emerge from enormous patience. That answer may sound less dramatic than, "We discovered a wall in space." But in truth it is more impressive, because the wall is vast. Yet the method that found it began with tiny photons arriving one by one. There is a comfort in that. Many difficult things yield not to force, but accumulation. Small signals, repeated effort, careful mapping. That applies to science and occasionally to life. Perhaps today felt too large to understand all at once. Perhaps some problems seem sprawling and shapeless. The universe offers a gentle reminder that even billion light-year puzzles are approached piece by piece. One measurement, one point, one pattern at a time. And now that we know how astronomers locate such immense structures, another question naturally waits nearby. What does the map itself actually look like when the invisible universe begins to take shape? There is something wonderfully strange about the phrase mapping the invisible universe. It sounds like a task given to a wizard, or perhaps to an intern who should have asked more follow-up questions. After all, maps are usually made of things we can plainly see. Roads, coastlines, rivers, borders, mountain ranges, hiking trails that looked easier on paper, and cafes whose opening hours seem based on private philosophy. A map, in ordinary life, is a guide to visible terrain. But astronomy asks us to make maps of realities that cannot be viewed in any direct, comfortable sense. We cannot step outside the universe with a notebook. We cannot rise above the galaxies in a helicopter. We cannot glance down from some celestial balcony and say, "Ah, yes, the filaments are clearer from this angle." Instead, we remain here on one small planet beneath one atmosphere, using fragments of incoming light and the patient tools of inference. And somehow, that is enough. When astronomers talk about mapping the universe, they are rarely speaking of drawing stars exactly as they appear to the eye. The deeper goal is to understand structure, where matter gathers, where it thins out, how galaxies cluster, how space expands, how patterns stretch across scales too large for intuition. To do that, scientists must work with what can be detected, even when much of what matters cannot be seen directly. That includes one of the most influential ingredients in cosmic structure, dark matter. Dark matter does not shine, glow, sparkle, reflect, twinkle, or politely announce itself. It does not emit light that telescopes can photograph in the ordinary sense, yet its gravity influences galaxies, bends light, and helps shape the cosmic web. So right away, our map is unusual. We are tracing visible islands to understand invisible continents. That may sound frustrating, but human beings have long experience with indirect knowledge. You cannot see wind, yet you map it by movement. You cannot see gravity itself, yet you infer it from falling things and orbiting worlds. You cannot see someone's patience, though waiting beside a slow-loading computer can reveal impressive amounts of it. Science often advances by studying effects rather than appearances. The universe, fortunately, leaves clues everywhere. Let us begin with the most familiar clue: light. Every star, galaxy, nebula, and quasar sending photons across space is effectively mailing information outward in all directions. Some of that information eventually reaches Earth. It arrives weakened, ancient, and sometimes after a journey longer than multicellular life has existed here. Still, it arrives. Telescopes collect that light, concentrate it, and pass it to instruments that measure brightness, color, spectrum, motion, and position. One object becomes many data points. Repeat this enough times, and the night sky stops being scenery. It becomes a database. That transformation is one of the quiet revolutions of modern astronomy. The stars inspired wonder for thousands of years. They still do. But now they also populate catalogues, coordinate systems, velocity maps, redshift surveys, and three-dimensional reconstructions. We did not lose the romance of the sky. We simply added spreadsheets. Somewhere, that sentence should be embroidered on a lab coat. Now, a flat image of the sky is only the beginning. If you photograph 10 galaxies, you know where they appear on the sky, but not how far away they are from one another in depth. Two galaxies may look adjacent while being separated by vast distances. This is why mapping the invisible universe requires the third dimension. And distance in astronomy often comes through redshift. As the universe expands, light travelling through it is stretched. Its wavelengths lengthen, shifting toward the red end of the spectrum. By measuring this shift, astronomers estimate how far away distant galaxies are and how fast cosmic expansion has affected their light. That means each galaxy can be placed not just left or right, up or down, but nearer or farther. With enough measurements, a three-dimensional map emerges. Now imagine plotting hundreds of thousands of galaxies, then millions. At first, one might expect a mist of scattered dots. Instead, something startling appears. Galaxies are not evenly distributed like dust in a beam of sunlight. They gather into clusters. Clusters connect through filaments. Vast, empty voids open between them. Dense nodes anchor strands of matter that stretch for enormous distances. The resulting pattern resembles foam, roots, lace, veins, or the branching network of life seen under a microscope. Again, these are comparisons of shape, not identity. The universe is not a cabbage leaf, though from far enough away many things become suspiciously similar. This grand arrangement is called the cosmic web, and mapping it is one of the greatest cartographic achievements in history. Think of earlier maps humans made. Coastlines once unknown became charted, mountain passes were traced, oceans were crossed and measured, continents gained outlines. Now compare that to modern cosmology. We are charting regions no ship can sail to, no foot can cross, no flag can claim, and no tourist office can sensibly promote. That is progress of a peculiar and admirable kind. But we should be honest about the challenge. The map is incomplete. It will always, in some sense, be incomplete. The observable universe contains only the portion from which light has had time to reach us since cosmic history began. Beyond that horizon, there may be more structure, more galaxies, more everything. We do not know the full extent. Even within what we can observe, faint objects escape detection, dust obscures some regions, instruments have limits, and time itself complicates matters because distant objects are seen in earlier states. So cosmic maps are both powerful and provisional. They improve as tools improve. This is not a flaw. It is the normal rhythm of science. Each generation redraws the edges with better ink. Now let us return to the invisible part. Dark matter cannot be seen directly with telescopes, yet astronomers map its distribution through gravitational effects. One method is gravitational lensing. Mass bends space-time, and light passing near mass follows that curvature. When light from distant galaxies travels past foreground matter, the images can be distorted, magnified, stretched, or multiplied. By studying these distortions statistically across many galaxies, scientists infer where mass must be located, including unseen dark matter. It is an extraordinary trick. We use bent light to map invisible gravity. Had someone proposed this casually in our village square centuries ago, reactions would likely have been mixed. Yet today it is standard astrophysics. Another method comes from galaxy motions. Galaxies within clusters move faster than visible matter alone can explain. Rotation curves of galaxies show stars orbiting in ways suggesting far more mass than we can see. Visible matter provides part of the story. Dark matter fills in much of the rest, so our maps become layered. There is the luminous map of stars and galaxies. There is the inferred mass map shaped by gravity. There is the expansion map revealed by redshift. There is the relic map of the early universe preserved in the cosmic microwave background. Each is a different lens on one reality. This layered understanding resembles how we map Earth. There are political maps, topographic maps, weather maps, geological maps, transit maps, and ecological maps. None alone tells the whole story. Together they reveal complexity. Likewise, no single cosmic map explains the universe, but combined they begin to show texture. Now consider the emotional effect of all this. When people imagine the universe, many picture emptiness sprinkled with stars. That image is not wrong, but it is incomplete. The mapped universe is organized emptiness. Matter gathers where gravity encourages it. Voids widen where less matter resides. Expansion stretches everything. Ancient fluctuations from the early universe grow into modern structure. The cosmos is not random static. It has memory. Tiny density differences in the young universe became the seeds of galaxies and walls and filaments billions of years later. In that sense, cosmic maps are records of growth. A wrinkle became a cluster. A slight excess became a supercluster. A faint imbalance became architecture. There is something reassuring in that. Great structures can begin from tiny differences amplified patiently over time. That principle is not limited to cosmology. Now practical challenges remain. Telescopes on Earth must look through atmosphere, which blurs images and absorbs some wavelengths. Light pollution brightens the sky. Weather interferes. Instruments require calibration. Data must be processed carefully. Even after collection, maps are not self-explaining. Computers help identify patterns, estimate uncertainties, and visualize three-dimensional distributions. Scientists debate methods. Where exactly is a filament? How connected must regions be before calling them one structure? What smoothing scales are appropriate? These questions are technical, but they matter deeply. Maps are interpretations as well as measurements. That is true whether drawing coastlines or galaxy walls. The Boss Great Wall, for example, emerged from this larger cartographic effort. Without vast redshift surveys and sophisticated analysis, it would remain hidden within scattered points of light. Seen individually, galaxies are objects. Mapped collectively, they become geography. That sentence captures much of modern cosmology. Now, if all this feels oddly calming, there may be a reason. Maps reduce confusion. They do not eliminate mystery, but they turn wilderness into pattern. They say, there is structure here, even if it is large and difficult. Human minds seem to like that. Perhaps you do too. Perhaps there is comfort in knowing that beyond tonight's small concerns, there exists a universe whose invisible scaffolding can still be traced by patient minds. No single person sees the whole thing. No one holds the final map. Yet together, through generations of measurement, correction, imagination, and evidence, we sketch something true, and the sketch keeps improving. There comes a point in nearly every discussion of astronomy when numbers stop being helpful. At first, they feel useful and respectable. Earth is about 12,742 kilometers wide. The Moon is roughly 384,000 kilometers away. The Sun sits about 150 million kilometers from us. These are large figures, certainly, but they still belong to a category the human mind can wrestle with. They can be compared to journeys, maps, flights, and unfortunate commutes. Then space clears its throat. Soon we meet distances so extreme that ordinary language begins to wobble. Stars measured in trillions of kilometers, galaxies spanning hundreds of thousands of light years, neighboring, galaxies millions of light years away, clusters of galaxies tens of millions, walls and filaments hundreds of millions or billions. At that stage, numbers continue functioning mathematically, but psychologically they become decorative. We can say them, we cannot feel them, and that is the scale problem. The Boss Great Wall lives firmly inside that problem. To hear that something stretches for around 1 billion light years sounds impressive, but the phrase often lands in the mind the same way a very large phone number does. You recognize magnitude abstractly, yet no inner picture forms. The imagination, finding no handles to grip, politely excuses itself. This is not a personal failing, it is biology. Human intuition evolved for nearby scales. Distances to water, distances to shelter, distances to fruit, weather, family, danger, or the nearest place selling bread. Our ancestors did not need a deep emotional grasp of megaparsecs. They needed to know whether that rustling bush contained berries or consequences. As a result, we are excellent at mid-sized reality. We understand a room, we understand a road. We understand the walk from bed to kettle in low light with varying levels of success. But cosmic size is another matter entirely. Let us begin gently. A light year is the distance light travels in 1 year. Light moves at roughly 300,000 kilometers per second. In 1 second it circles Earth several times. In about 8 minutes it reaches the Sun. In just over a second it reaches the Moon. Fast enough, one might think, to win most races. Now allow that speed to continue not for seconds or minutes, but for a full year. That is 1 light year. Already most minds begin to soften around the edges. Now multiply it by 1 billion. That is the sort of scale invoked when discussing the Boss Great Wall. To cross such a span at the speed of light would require 1 billion years, not 1 billion in the casual sense people sometimes use to describe waiting for software updates, but an actual billion years. 1 billion years ago on Earth, multicellular life was still far in the future. Continents looked different. Oceans were different. Air was different. Nothing recognizably human existed, nor anything remotely interested in astronomy. If light had set out then from one side of such a structure, it would only now be arriving at the other. This is the kind of comparison that helps briefly, then collapses under its own enormity. Another difficulty with cosmic scale is that large numbers blur together. To many people, 1 million and 1 billion both simply mean very large. Yet the difference is dramatic. 1 million seconds is about 11.5 days. 1 billion seconds is more than 31 years. That is the gap hidden between two words we often treat as neighbours. Likewise, a galaxy 1 million light-years away and a structure 1 billion light-years across are separated by conceptual oceans. The universe exploits this weakness in our intuition constantly. Now consider the Milky Way. Our galaxy spans roughly 100,000 light-years, already immense beyond practical comprehension. If the Milky Way were reduced to the size of a dinner plate, the solar system would be microscopic. Earth itself would become less an object than an accounting inconvenience. Yet the Boss Great Wall is vastly larger still, composed not of stars in one galaxy, but of galaxy superclusters and filaments spread across scales, where galaxies themselves become dots in a pattern. This introduces a curious inversion. At everyday scales, cities contain buildings, buildings contain rooms, rooms contain furniture. At cosmic scales, walls contain superclusters, Superclusters contain clusters, clusters contain galaxies, galaxies contain stars, stars may contain planets, planets may contain someone trying to imagine the wall. Reality nests beautifully. But the farther we zoom out, the more meaning changes. For example, density. When people hear of a giant wall in space, they often imagine crowding packed matter, congestion, perhaps celestial traffic complaints. In truth, even dense cosmic structures are mostly emptiness. Galaxies remain separated by enormous gulfs. Space dominates everything. So the Boss Great Wall is huge without being solid. It is massive without being compact. It is structured without being built. Again, language strains. This happens because many human words were designed for houses, fields, bodies, weather, tools, and social life. They were not optimized for billion light-year statistical overdensities, yet we keep using them bravely. Another reason size stops making sense is that we mistake visibility for significance. Mountains feel large because we can stand beneath them. Oceans feel vast because we can cross shorelines and watch horizons. But cosmic structures exceed sensory confirmation. No one stands beside the Boss Great Wall. No traveller sees it stretch into distance. It exists primarily through mapping, data, and inference. That makes it cognitively slippery. The Eiffel Tower feels real instantly. A billion light-year wall of galaxies requires trust in evidence and comfort with abstraction. Modern science asks for both. There is also the time component. When we observe faraway galaxies, we see old light, so a giant structure mapped across vast distances is also spread across history. Different regions are observed at different cosmic moments depending on distance. The map is not just large in space, it is layered in time. This can make the mind quietly give up and focus on snacks. Still, let us continue. Suppose you wanted to travel across the Boss Great Wall in a spacecraft moving at the speed of the fastest probes humanity has built. It would take so long that civilizations could rise, flourish, vanish, and leave archaeological mysteries before you had made meaningful progress. Even light, the universe's speed champion, requires 1 billion years. Our usual travel metaphors become useless here. No road trip compares. No voyage compares. Even saying journey begins to sound optimistic. So how do scientists cope with such scales? They use units, models, visualizations, and ratios. Astronomers often prefer parsecs and megaparsecs. Cosmologists compare structures statistically. Computer simulations shrink cosmic volumes into understandable graphics. Researchers think in distributions, not scenic impressions. In other words, they do what humans always do when reality exceeds intuition. They build tools. Mathematics is one such tool. It lets us handle truths we cannot picture directly. You do not need to emotionally feel 1 billion light years for equations about structure formation to remain valid. Nature does not require your imagination's approval. That is comforting in its own way. The stars continue whether or not we grasp them fully. There is another subtle scale problem worth noticing. When something becomes too large, we sometimes assume it must be central or dominant. But the Boss Great Wall, despite its enormous extent, is one structure among many in a vast observable universe. It is remarkable, yes, but not the centre of everything. Large does not equal privileged. That lesson appears often in astronomy. Earth is not the centre. The Sun is not the centre. The Milky Way is not the centre. Even gigantic walls of galaxies are not the centre. Reality seems fond of decentralization. This can feel humbling or freeing depending on mood. Now let us bring this closer to home. Your own life unfolds on scales where seconds matter, meters matter, years matter, a missed train matters, a kind word matters, sleep matters. Whether you remember to answer that message may matter more than any supercluster tonight. Cosmic scale does not erase human scale. They coexist. The Boss Great Wall can stretch across unimaginable distances while your present moment still contains the practical universe of breathing, resting, listening, and being here. That coexistence is one reason astronomy soothes many people. It places our concerns in perspective without declaring them meaningless. Small is not trivial. Large is not urgent. Both are simply scales of reality. There is also something reassuring in admitting confusion. You're not meant to intuitively grasp a billion light years any more than a fish is meant to understand mountaineering. Some truths are approached indirectly. We learn them through symbols, comparisons, and shared effort. That is enough, and perhaps better than enough. Because wonder often begins exactly where comprehension becomes thin. The Boss Great Wall is difficult to imagine not because it is vague, but because it is real on terms larger than instinct can comfortably host. So when size stops making sense, we need not panic. We can let sense change shape. We can trade vivid pictures for careful understanding. We can accept that some realities are known best by proportion, relation, and pattern rather than by inner imagery. If structures this immense are made of countless galaxies, what happens when galaxies themselves stop being majestic individual worlds and start becoming mere dots on a cosmic map? There is a curious threshold in astronomy where familiar wonders become background details. A galaxy, for instance, is already an astonishing thing. It can contain hundreds of billions of stars, vast clouds of gas and dust, dark matter, halos, ancient globular clusters, supernova remnants, wandering planets, and often a supermassive black hole at its center. Entire generations of suns are born, live, and die within it. Spiral arms turn slowly over immense spans of time. Civilizations, if they arise, would likely spend ages just learning their own local neighborhood. By any ordinary standard, a galaxy should be enough. If one were placed on a table in miniature, it would command lifelong attention. Books would be written, museums would be built. People would gather around it whispering things like, "Look at the structure on that spiral arm." And yet, on the largest cosmic scales, galaxies become dots, not because they shrink in reality, but because our perspective expands. That shift is one of the most powerful lessons hidden inside structures like the Boss Great Wall. Size is relational. Importance is contextual. A thing can be immense in one frame and tiny in another. We know this principle from everyday life, though less dramatically. A city seems vast when walking across it. A country seems manageable on a map. A mountain range becomes wrinkles from an airplane window. Likewise, galaxies that feel unimaginably grand up close become plotting points when mapping billions of light years. This is not disrespectful to galaxies. It is geometry. Suppose you're looking at a forest from ground level. Trees dominate everything. Bark texture matters. Branches matter. Leaves catch the light. You notice roots, insects, sounds, weather, and the scent of soil. Rise high enough above that forest, and individual trees merge into canopy patterns. Clearings appear. Rivers become visible. The shape of the whole landscape emerges only after details soften. Neither view is wrong. They answer different questions. Astronomy works exactly this way. If you want to understand star formation, black holes, galactic collisions, or the chemistry of planetary systems, then galaxies must be studied as rich individual worlds. If you want to understand the architecture of the universe, galaxies become markers. They are lights pinned to a larger structure. That is where walls, filaments, clusters, and voids come into focus. The Boss Great Wall is one such focus. It is not remarkable because a single galaxy within it is unusual. It is remarkable because many galaxies taken together reveal a pattern of extraordinary scale. This distinction matters deeply. Human attention is naturally drawn to objects. We notice singular things: one mountain, one whale, one comet, one person entering a room dramatically late. But nature often organizes itself through systems rather than singulars. A termite mound is impressive. But the colony is the real phenomenon. One neuron matters, but the network creates thought. One water molecule is trivial, but enough together create waves, storms, currents, climate. Likewise, one galaxy is magnificent, but many galaxies together reveal cosmic structure. When astronomers map the large-scale universe, they're often less interested in any single galaxy than in the statistical arrangement of many. Where are galaxies denser than average? Where are they sparse? How are clusters connected? What shapes emerge over hundreds of millions of light years? Once enough data accumulates, the dots begin speaking. They tell us gravity has been at work for billions of years. They reveal where matter gathered more strongly after the early universe. They expose hidden scaffolding likely shaped by dark matter. They show that the universe is not a random scatter, but textured and organized. This is one reason survey astronomy became so transformative. Earlier eras of astronomy often focused on specific objects: planets, stars, nebulae, notable galaxies. Modern cosmology increasingly asks population questions. Not, what is this galaxy doing? But, what are millions of galaxies doing together? That shift resembles moving from biography to sociology. Both are valuable. They simply operate at different scales. Now, there is something emotionally interesting about seeing galaxies reduced to dots. Some people find it diminishing. They imagine that if the Milky Way becomes one point among countless others, then perhaps grandeur is lost. I would suggest the opposite. When galaxies become dots, we do not lose wonder. We relocate it. The wonder moves from the object to the pattern. Instead of marvelling at one spiral galaxy, we marvel at the web formed by many. Instead of admiring one jewel, we admire the mosaic. This happens in other fields too. One musical note is simple. A symphony lies in arrangement. One tile may be plain. A mosaic can stop you in your tracks. One word is ordinary. A sentence may stay with you for years. Scale changes what beauty looks like. The Boss Great Wall invites exactly this change. Its galaxies, clusters, and superclusters are components. The astonishment lies in their combined geometry. And geometry, when stretched across the universe, can feel surprisingly intimate. Patterns are how minds understand complexity. We look for constellations in stars, faces in crowds, meaning in repetition, roads in maps, rhythm in footsteps. Pattern recognition is one of our oldest mental talents. Sometimes it misfires, admittedly. This explains several conspiracy theories and at least some wallpaper choices. But often it serves us brilliantly. Without pattern recognition, the Boss Great Wall would remain just data points. With it, structure emerges. Of course, scientists are careful here. Human beings can see patterns where none exist, so astronomy uses statistics, modelling, and rigorous methods to distinguish genuine structure from random clustering. The wall is not a fantasy shape sketched into noise. It is a measurable, large-scale concentration. Still, the deeper principle remains. Reality becomes legible through arrangement. Now consider the universe from multiple zoom levels. At one scale, a planet matters. At another, a solar system matters. At another, a galaxy. Then a cluster. Then a supercluster. Then a wall. Then perhaps the distribution of walls and voids across still larger regions. Knowledge changes with zoom. This is worth remembering outside astronomy too. Many disagreements in life are scale disagreements in disguise. One person is looking at the tree, another at the forest. One notices immediate detail, another long-term pattern. Both may hold part of the truth. The cosmos rehearses this lesson constantly. Now let us talk briefly about voids, because walls make more sense beside emptiness. Large cosmic structures are not simply dense regions added onto an otherwise full universe. They are partly defined by contrast with enormous underdense spaces called voids. These regions contain far fewer galaxies than average. Some span hundreds of millions of light years, so walls and filaments are shaped not only by what is present, but by what is absent. Again, a familiar principle. A melody depends on silence between notes. A city skyline depends on open sky around it. Writing depends on blank space as much as ink. The Boss Great Wall gains identity partly because nearby regions are less crowded. Patterns need contrast. There is also humility in realizing that if we were located elsewhere, some structures might appear differently or remain unnoticed. Perspective matters. Mapping depends on position, data quality, and available light. We do not observe the universe from nowhere. We observe from here. That small word here carries a lot of weight. Here means one planet orbiting one star in one galaxy, among many dots participating in larger patterns. Yet from here, we discovered those patterns anyway. That may be one of humanity's finest habits, being local creatures with non-local curiosity. Now imagine standing inside a galaxy within the Boss Great Wall. You would not feel inside a wall. You would see local stars, neighbouring galaxies perhaps, ordinary, celestial scenery. The larger pattern only appears from far enough away. This too has echoes in life. Many systems are invisible from within them. Economies, climates, cultures, ecosystems, traffic patterns, historical eras. Participants feel daily details. Broader structure appears only through distance and data. Astronomy simply presents the grandest version of that truth. So galaxies as dots is not a reduction. It is a transformation of viewpoint. It says that things retain their richness locally while contributing to something larger globally. You are composed of cells. A city is composed of people. A forest is composed of trees. A wall of galaxies is composed of galaxies, meaning lives at multiple levels simultaneously. That is one reason the universe remains endlessly interesting. No single scale exhausts it. At the level of stars there is drama. At the level of galaxies there is evolution. At the level of walls there is architecture. And now that we've learned how individual galaxies become points in a much larger design, another question quietly follows. If these giant patterns exist at all, what kind of universe produces webs, strands, and walls instead of smooth, even emptiness? When most people picture the universe, they imagine something like scattered glitter on black velvet, stars sprinkled through darkness, galaxies floating separately, a few dramatic nebulae for decoration, plenty of empty space in between. It is a perfectly understandable mental image, and for many purposes it works well enough. But once astronomers began mapping galaxies on the larger scales, that picture started to change. The universe, it turns out, does not merely look sprinkled, it looks structured. Not rigidly structured, not neatly gridded, not arranged according to some cosmic interior designer with strong opinions about symmetry. Instead, it looks textured. It looks interconnected. It looks like matter has gathered into strands and sheets surrounding vast emptier regions. And to many scientists, one of the most natural visual comparisons is foam. Not because the cosmos is filled with soap, although that would make telescope maintenance unexpectedly interesting. Rather, because when bubbles cluster together, they create thin walls and edges around pockets of emptiness. The pattern is cellular. Boundaries meet. Open spaces are enclosed by networks. When astronomers map galaxies across enormous distances, something similar appears. Dense filaments and walls of matter surround giant voids, where relatively few galaxies reside. The result can resemble a three-dimensional bubble structure spread across the observable universe. This comparison helps because foam is familiar. You have likely seen bubbles in a sink, sea foam on a shore, froth atop coffee, or that determined cluster of soap bubbles that survives every rinse cycle with suspicious confidence. Foam teaches us that space can be mostly empty while still having shape. That is exactly the lesson of the cosmic web. The Boss Great Wall is one striking feature within that broader foamy architecture. It is not a separate universe from the rest, but a prominent ridge, sheet, and clustering inside a much larger network. To appreciate why the universe looks this way, we need to go back to the beginning, or at least to a very early and energetic portion of it. The young universe was hot, dense, and remarkably uniform, but not perfectly uniform. Tiny fluctuations in density existed. Some regions contained slightly more matter than others. These differences were incredibly small, almost laughably subtle compared with the grand structures they would later produce. But gravity is patient. Give gravity enough time, and tiny advantages become large outcomes. Regions with slightly more matter exerted slightly more gravitational pull. That attracted more matter, making them denser still. Meanwhile, less dense regions lost material comparatively and became emptier over time. This process continued across billions of years. The result was not matter collapsing into one giant lump, because expansion of the universe and the distribution of motion complicated the story. Instead, matter flowed into networks, sheets formed, filaments stretched between dense nodes, voids widened where material drained away. What began as faint irregularities became architecture. There is something deeply soothing in that progression. Small differences given time became shape. The universe did not need haste. Now let us imagine zooming outward gradually. At the scale of planets, we care about mountains, oceans, weather, seasons. At the scale of stars, we care about fusion, gravity, life cycles, planetary systems. At the scale of galaxies, we care about spiral arms, collisions, dark matter halos, star formation histories. Keep zooming out farther, and galaxies themselves become points. Their internal details fade. What remains is position. Once enough positions are plotted, the foam appears. This shift can feel surprising because our everyday intuition assumes that if you zoom out enough, detail disappears into smoothness. Sometimes that is true. A forest from a plane becomes green texture. A city from orbit becomes lights and shapes. Yet with the universe, zooming out reveals a new level of order. The dots organize into cells. That is one reason cosmology can feel so rewarding. It keeps changing the question when you think you know the answer. Now, a careful note. The universe does not look exactly like soap foam in every scientific sense. Real foam obeys fluid dynamics, surface tension, pressure relations, and chemistry specific to bubbles. Cosmic structure grows through gravity, expansion, dark matter, and the history of primordial fluctuations. The comparison is visual and conceptual, not literal. Still, analogies matter when dealing with scales beyond instinct. Foam helps us picture a space that is mostly empty but not random. That phrase deserves repeating. Mostly empty but not random. Many people hear space is empty and imagine blankness. But emptiness can have geometry. Consider a honeycomb. Much of it is air, yet the emptiness is arranged. Consider a city. Much of it is open volume between buildings, yet roads and districts give structure. Likewise, cosmic voids are not just missing matter. They are part of the pattern matter creates by not being there. This means absence is informative. The vast voids between filaments tell us where matter flowed from, how gravity evolved regions, and what the early universe must have been like. Empty places help define full places. There is a gentle philosophical lesson there too. Sometimes what is missing shapes what remains. Now let's talk about those voids for a moment. Cosmic voids can span tens to hundreds of millions of light years. They're among the largest recognizable features in the universe. Inside them, galaxies are sparse. Not non-existent, but far less common than average. If you lived in a galaxy deep inside a void, the surrounding cosmic neighborhood would appear lonelier. Fewer nearby galaxies, less crowded scenery, a quieter address, cosmically speaking. Meanwhile, along filaments and walls, galaxies are more numerous. Clusters gather at intersections where strands meet, much like cities forming at crossroads. Again, the comparison to human geography is only partial, but useful. Road networks channel movement. Gravitational networks channel matter. The Boss Great Wall can be understood as one especially grand concentration within this larger foam-like layout. It is impressive not because it violates the pattern entirely, but because it exemplifies it on remarkable scale. Large ridges stand out within landscapes, long strands stand out within webs, great walls stand out within cosmic foam. There is another reason scientists value these patterns. They test cosmological models. Computer simulations of the universe begin with early density fluctuations inferred from observations such as the cosmic microwave background. Then gravity, expansion, dark matter, and known physics are allowed to evolve the system forward. When simulations produce networks resembling observed galaxy distributions, confidence grows that we understand key ingredients of cosmic history. When observations surprise us, confidence becomes curiosity. Either outcome is useful. The universe is an excellent examiner. Now imagine the emotional contrast between everyday life and these scales. Perhaps today involved emails, errands, appointments, dishes, weather, or deciding whether laundry can be considered a future problem. All valid human concerns. And yet beyond those immediate tasks lies a universe whose matter arranged itself over billions of years into foam-like cells spanning incomprehensible distances. This perspective does not diminish daily life, it enriches it. You exist within a reality large enough to contain both grocery lists and galactic walls. That is no small thing. There is also comfort in the patience of cosmic processes. Nothing about this structure formed in a hurry. No sudden dramatic flourish assembled the web overnight. Gravity worked slowly. Expansion continued steadily. Matter drifted, clustered, merged, and reorganized over ages. The universe often prefers long timelines. Perhaps we can borrow that patience occasionally. Now, another subtle point. When we say the universe looks like foam, we mean from the perspective of mapped matter distribution. If you travelled through it, you would mostly encounter darkness punctuated by galaxies. You would not float through visible glowing bubble boundaries. Maps reveal truths not obvious from within. A city map shows neighbourhoods invisible from sidewalk level. A weather map shows fronts invisible from your window. A cosmic map shows foam invisible from any single galaxy. This is why science depends so much on representation. Reality often needs translation before it becomes understandable, and human beings are surprisingly good translators when motivated. We took faint photons from distant galaxies and turned them into cosmic geography. That remains extraordinary. If the universe looks like foam when viewed on the grandest scales, then naturally we must ask what forms the boundaries of those bubbles. What are the strands? What are the bridges between clusters? What are the immense lines along which galaxies gather like dew on invisible wires? Astronomers call this vast network the cosmic web, and it may be one of the most revealing names in modern science. A web suggests connection. It suggests tension. It suggests that what appears separate at first glance may actually belong to a larger structure. It also suggests that if you walk into it carelessly, you may spend several minutes flailing and apologizing, though fortunately the cosmic version is harder to stumble into accidentally. The cosmic web is the large-scale arrangement of matter across the universe. Galaxies do not sit randomly in empty space like raisins tossed into darkness. They tend to cluster along enormous filaments, gather in dense nodes where filaments intersect, and leave behind vast voids with comparatively little matter. These filaments are the threads of everything. Not everything in the literal sense, of course. They do not contain your keys, lost emails, or that missing lid from the food container drawer. But they do help organise the distribution of galaxies, galaxy clusters, gas, and much of the visible large-scale structure we observe. And crucially, much of this web is shaped by something invisible. Dark matter. Now, dark matter is one of those phrases that sounds dramatic enough to belong in fiction, yet remains entirely respectable science. It does not mean evil matter, moody matter, or matter that listens only to jazz after midnight. It simply refers to matter we do not observe directly through emitted light, but whose gravitational influence is strongly evident. Galaxies rotate in ways suggesting more mass than visible stars and gas can explain. Galaxy clusters hold together more strongly than ordinary matter alone would allow. Light bends around unseen concentrations of mass. Across many observations, the same conclusion appears. There is more matter present than we can see, and this unseen matter plays a starring role in the cosmic web. To understand why, we need to travel mentally back to the early universe. After the Big Bang, the universe was hot, dense, and expanding. Tiny fluctuations in density existed throughout that young cosmos. Some regions held slightly more matter than others. These differences were extremely small, but small beginnings often matter more than they first appear. Dark matter, because it does not interact strongly with light the way ordinary matter does, could begin clumping gravitationally relatively early. It helped create gravitational wells, subtle valleys in the landscape of space where matter would later gather. Ordinary matter, the material that becomes stars, planets, people, oceans, sandwiches, and telescopes, then fell into these wells over time. In this way, dark matter acted like hidden scaffolding. Visible matter followed. That image is worth lingering on. Imagine walking into a building under construction. Before walls, paint, windows, and furniture appear, there is a frame. Beams define shape long before decoration arrives. Likewise, the cosmic web's visible galaxies may be the illuminated surfaces of a deeper invisible framework. The filaments we map through galaxies likely trace dark matter structures extending across enormous distances. So when astronomers observe strands of galaxies connecting clusters, they're also seeing hints of something larger and mostly unseen. There is a certain elegance in that arrangement. Light reveals darkness indirectly. Now let us talk about the parts of the web. First, there are nodes. These are dense intersections where multiple filaments meet. In such places, galaxy clusters often reside. Clusters can contain hundreds or thousands of galaxies bound together by gravity, along with hot gas and dark matter. They are among the largest gravitationally bound structures in the universe. If the cosmic web were a transport network, nodes would be major cities. Then there are filaments. These are elongated structures stretching across tens to hundreds of millions of light years, containing galaxies, gas, and dark matter. Matter tends to flow along these filaments toward denser nodes over cosmic time. If nodes are cities, filaments are highways. Then there are sheets, or walls. These are broader planar concentrations of matter, often linking multiple filaments and clusters into large coherent regions. Structures like the Boss Great Wall belong in this category of especially large-scale connected features. And finally, there are voids, enormous underdense regions where relatively few galaxies reside. They are not empty in an absolute sense, but compared with the filaments and nodes, they are sparse. If the web is a city map, voids are the wide-open countryside between crowded corridors. This architecture did not appear suddenly. It emerged gradually through gravity acting over billions of years. That patience matters. Modern life often trains us to expect instant outcomes. Load now, deliver now, reply now, improve now. But the universe remains committed to the long version of events. Filaments formed slowly, clusters assembled through mergers and inflow. Voids widened as matter drained outward. Walls developed as regions linked. The cosmic web is a monument to accumulation. Now one might ask whether these threads are physically tangible. Could you travel through a filament and notice you were inside one? Not in the cinematic sense. There would be no glowing lane markers or sign reading "Welcome to Filament 7. Space would still be mostly vast emptiness between galaxies. But statistically, the density of matter and galaxies would be higher than surrounding void regions. This is a recurring theme in cosmology. Many of the universe's greatest structures are real as patterns rather than as solid objects. A coastline is real though made of many grains. A forest is real though made of many trees. A traffic jam is real though no one built it intentionally. Likewise, a cosmic filament is real, though composed of distributed matter across immense space. Another fascinating point is that gas within filaments may contain a significant fraction of ordinary matter in the universe. For years, astronomers struggled with the missing baryon problem, meaning some ordinary matter predicted by cosmology was hard to locate. Evidence suggests much of it may exist as diffuse hot gas in filaments between galaxies, so the web does not merely organize galaxies, it may also store large amounts of matter between them. The threads are fuller than they first appear. Now let us return to the boss Great Wall. It is not separate from the cosmic web, it is one especially grand expression of it. A wall-like connected region made of superclusters and filaments within the larger network. This matters because extraordinary structures need not be anomalies. Sometimes they are natural extremes within an ongoing process. A very tall tree still belongs to the forest. A very long river still belongs to the landscape. A very large wall still belongs to the web. Scientists study these extremes because they test expectations. How common should such structures be? How large can connected patterns grow under known physics? Do simulations produce similar features? The answers refine cosmology. Now, there is something emotionally grounding about the phrase threads of everything. Not because it means mystical unity or abstract sentimentality. We need none of that. The scientific truth is sufficient. Matter is distributed relationally. Galaxies are not isolated curiosities sprinkled randomly in emptiness. They participate in a larger gravitational history. Their locations reflect ancient fluctuations, dark matter scaffolding, expansion, mergers, and time. They belong to context. So do we. Every human life also exists in webs. Families, cities, languages, ecologies, histories, economies, friendships, causes and effects extend in farther than daily awareness usually notices. Perhaps that is one reason the cosmic web resonates. It mirrors a general truth. Isolated appearances often hide connected realities. Now imagine looking outward from Earth. We orbit one star in one galaxy called the Milky Way. That galaxy belongs to a local group of galaxies. That group lies near larger structures and participates in broader distributions connected through the cosmic web. Even our cosmic address is layered. You're not merely on Earth. You're in a solar system, in a galaxy, in a local grouping, within a vast network of matter shaped over billions of years. Quite a mailing label. And yet, despite all this grandeur, tonight may simply consist of breathing quietly and listening to a voice describe invisible filaments while your room remains pleasantly ordinary. That contrast is lovely. The largest known structures and the smallest comforts coexist without conflict. If these immense threads were built by gravity over unimaginable time, how exactly does gravity manage such architecture with nothing but patience and mass? If the universe were run by dramatic forces alone, it might look very different. There would be fireworks everywhere, constant collisions, sudden transformations, and perhaps a general sense that someone important was always making an entrance. To be fair, the cosmos does contain explosions, black holes, gamma-ray bursts, and stars that end their lives with admirable theatrical flair. But when it comes to the largest structures in existence, the true builder is not drama, it is patience. And the tool most responsible for that patient construction is gravity. Gravity is easy to underestimate because in daily life it feels ordinary. It keeps feet on floors, rain moving downward, cups from floating away, and toast from escaping breakfast plates. We become so accustomed to it that it can seem almost boring. Yet gravity is one of the great sculptors of reality. Given enough time, it gathers dust into planets, gas into stars, stars into galaxies, galaxies into clusters, and clusters into the sprawling architecture of the cosmic web. The Boss Great Wall is one result of that long labour. No cosmic cranes were involved. No celestial engineers in helmets unfolded blueprints across intergalactic tables. There was no urgent schedule, no ribbon-cutting ceremony, no grand announcement that construction would begin at dawn. There was only matter, time, and gravity working slowly. That slowness matters. Many forces in nature act quickly. Fire spreads quickly, sound travels quickly. Chemical reactions can happen quickly. Human opinions on the internet happen with astonishing speed. Gravity, by contrast, often prefers long timelines. It is relatively weak compared with some other fundamental forces. A small refrigerator magnet can lift a paperclip against the pull of the entire Earth. That is not because Earth lacks confidence. It is because electromagnetism can be much stronger at small scales. So why does gravity dominate the large universe? Because gravity has two habits that make it powerful over time. First, it is always attractive. It pulls mass toward mass. Second, it acts across vast distances. There is no negative mass casually cancelling it in the way positive and negative electric charges can balance. Matter accumulates. Pull reinforces pull. Tiny differences grow. That makes gravity less like a punch and more like a tide. It may not win by speed, it wins by persistence. To understand gravity's slow architecture, let us return to the early universe. After the hot beginning of cosmic expansion, matter was spread remarkably evenly, but not perfectly. Tiny density fluctuations existed. Some regions were ever so slightly denser than others. These differences were minute. If you had looked then, you might not have predicted future galaxy walls from such modest irregularities. But gravity noticed. A slightly denser region exerts slightly more pull. That extra pull draws in nearby matter. More matter increases density. Greater density increases pull. The process feeds itself. Over time, small imbalances become substantial structures. This is one of the deepest themes in cosmology. Large outcomes from tiny beginnings. The young universe contained seeds. Gravity supplied patience. Now, expansion complicates the picture. The universe is not static, space itself expands. Galaxies on average move farther apart over large scales, so gravity is building structure while expansion is stretching the arena. This creates a kind of cosmic competition. Where matter is dense enough, gravity can gather it locally. Where matter is sparse, expansion carries regions farther apart. The result is not one universal collapse or one universal smoothing, but patterned growth. Clusters form in some places, voids widen in others. Filaments connect dense nodes. Walls emerge where matter flows into sheets and ridges. The cosmic web is what happens when attraction and expansion negotiate for billions of years. There is something quietly elegant about that. Reality often emerges from competing tendencies held in balance. Now consider how galaxies form. Gas falls into dark matter halos, those gravitational wells shaped largely by unseen matter. As gas compresses, it cools, condenses, and forms stars. Small systems merge into larger ones. Galaxies collide, interact, distort, and grow. At every stage, gravity guides the choreography. Not always gently. Galactic mergers can be spectacular. Tidal tails stretch across space. Gas clouds compress into bursts of star formation. Central black holes may eventually merge in dances so extreme they send ripples through space-time. Still, even these dramatic episodes are nested inside a slower story. The great architecture took ages. Now let us think in terms of building styles. Human construction often begins with a plan. Foundations first, walls next, roof later. Someone eventually realizes they forgot one crucial pipe. Gravity does not work that way. It has no foresight. It does not aim for elegance. It simply follows laws. Yet from repeated lawful behavior, structure appears. This is common in nature. Snowflakes are not designed by tiny artisans. River deltas are not sketched in advance. Tree roots do not consult committee reports. Complex order can emerge from simple rules repeated patiently. The universe is full of such examples, but gravity's web may be among the grandest. Now, one reason giant structures like the Boss Great Wall fascinate scientists is that they test how far gravity's architecture can reasonably go. Given the age of the universe, the known rate of expansion, the properties of dark matter, and the initial fluctuations inferred from early cosmic signals, what sizes of connected structures should form? If we observe features larger or rarer than expected, cosmologists must ask careful questions. Are our models incomplete? Are definitions of connected structure influencing perception? Is this a rare but possible extreme? Have we underestimated ordinary processes? Science progresses through such tension. The universe does not hand out answer sheets. It hands out observations. Now, let us talk about timescales, because they are part of gravity's personality. The Moon orbits Earth in about a month. Earth orbits the Sun in a year. Stars orbit galactic centers over hundreds of millions of years. Galaxies merge over hundreds of millions to billions of years. Large-scale structure evolves over billions. Gravity rarely rushes the big projects. This can feel almost medicinal to consider. Much of human stress emerges from compressed time. Deadlines, schedules, delays, clocks, expectations. We live by hours and days. Meanwhile, the force shaping cosmic walls operates happily on billion-year calendars. It does not care if Tuesday was inconvenient. Another subtle feature of gravity is that it creates hierarchy. Dust grains gather into pebbles, pebbles into larger bodies, gas clouds into stars, stars into galaxies, galaxies into groups, groups into clusters, clusters into superclusters and networks. Each scale becomes building material for the next. The Boss Great Wall is not made from atoms directly. It is made from systems, made from systems, made from systems. Reality stacks itself upward. This hierarchical growth appears in many domains. Villages become towns, towns become cities, cells become tissues, notes become music. The universe seems fond of layered complexity. Now imagine standing in a quiet field at night. Gravity there feels simple. You feel weight. Perhaps you drop a pebble. Perhaps you sit down and notice the ground's reliable support. Nothing about that sensation hints at galaxy walls. Yet the same fundamental interaction keeping you anchored also helped gather matter into the largest patterns known. That continuity is beautiful. The ordinary and the immense share laws. There is no separate gravity for heroic scales, only the same one, acting longer. Another important point is that gravity does not work alone. Gas pressure, radiation, magnetic fields, dark energy, angular momentum, and many local processes matter too. But on the broadest scales of matter distribution, gravity is the principal organizer. It is the planner who never speaks, the architect who never sleeps, the mason who works only in deep time, and because it is so steady, it can be easy to miss. We tend to notice sudden change. A star exploding captures attention. A comet blazing overhead wins admiration. A black hole swallowing matter gets headlines. But the formation of a filament over billions of years passes without spectacle. Many essential processes do. Now there may be a lesson hidden there. Some of the most significant forces in life are not loud. Habits, routines, repeated kindness, gradual learning, persistent effort. These shape outcomes quietly, much as gravity shapes structure slowly. No need to romanticize it. Repetition simply matters. The universe demonstrates this at scale. Soon, however, another puzzle emerges. If gravity has had all this time to build vast structures, then why do some cosmologists still say formations like the Boss Great Wall should be surprising, or perhaps too large to comfortably expect? There is a special kind of scientific sentence that instantly captures attention. Theoretically, this should not exist. It is the sort of phrase that causes researchers to sit up straighter, sharpen pencils, open simulation files, and begin using words like interesting in tones that mean something far stronger than interesting. The Boss Great Wall often enters conversation through a version of that sentence, not because it floats in defiance of all known physics, not because it has broken mathematics in half and left equations sobbing quietly in a corridor, not because gravity has resigned in protest. Rather, structures like this are surprising because they seem uncomfortably large when compared with how cosmologists expect matter to smooth out on the grandest scales. That distinction matters. The Boss Great Wall does exist as an observed large-scale structure identified through galaxy survey data. The real puzzle is not existence versus non-existence. The puzzle is expectation versus observation, and science lives for puzzles of that sort. To understand why anyone would say something this large shouldn't exist, we need to revisit one of the working assumptions of modern cosmology, the cosmological principle. In simple terms, the cosmological principle says that when viewed over sufficiently large distances, the universe should be roughly homogeneous and isotropic. Homogeneous means matter is evenly distributed on average. Isotropic means the universe looks broadly the same in all directions on large scales. This does not mean every neighbourhood is identical, clearly not. Stars gather into galaxies. Galaxies gather into clusters. Clusters connect through filaments. Empty voids exist beside dense regions. Local lumpiness is expected, but zoom out far enough, and those lumps should statistically average into smoothness. Think of sand on a beach. Close up, every grain differs. Tiny ridges, shells, pebbles, footprints, suspicious gull activity. Yet from far enough away, the beach appears smooth. Cosmologists expected something similar from the universe. Small-scale irregularities, yes. Large enough scales, smoother averages. So when astronomers identify immense connected structures spanning hundreds of millions, or even billions of light years, an obvious question follows. How large can lumpiness remain before it becomes awkward? That is the heart of the matter. The Boss Great Wall is not the only giant structure to raise eyebrows. Other enormous formations such as the Sloan Great Wall and the Hercules Corona Borealis Great Wall candidate have also inspired discussion. Each one pushes on the boundary between expected clustering and unexpectedly grand coherence. Now let us be careful. When headlines say a structure shouldn't exist, they often simplify a much subtler scientific conversation. Scientists rarely mean impossible. They more often mean statistically surprising, model testing, sensitive to assumptions, or inconveniently enthusiastic. The universe is full of inconvenient enthusiasm. What researchers ask is whether structures of a given size and connectivity naturally arise, often enough within our best cosmological models. If they do, then the wall is dramatic but acceptable. If they are too rare, too large, or too coherent compared with simulations, then perhaps something in our understanding needs adjustment. That adjustment could involve theory, data interpretation, structure definitions, or simple statistical luck. All of these possibilities are scientifically normal. Now let us talk about simulations. Modern cosmology uses computer models that begin with early universe conditions, inferred from observations such as the cosmic microwave background. Tiny density fluctuations are seeded into virtual universes. Then gravity, dark matter behavior, expansion, and known physics evolve the system over cosmic time. The result is a simulated large-scale cosmos. Researchers then compare those simulations with actual galaxy surveys. Do we see similar cluster sizes, similar void distributions, similar filament networks, similar probabilities of giant walls? This is one of the great strengths of modern science. We do not merely speculate, we test. Sometimes simulations produce structures that look remarkably like what we observe. Sometimes they do not. Sometimes they produce analogues, but rarely. Sometimes the answer depends strongly on how one defines a connected structure. That last point is more important than it sounds. Nature does not attach labels. The universe does not announce, here ends one wall and here begins another. Humans identify patterns using thresholds, density criteria, linking lengths, clustering algorithms, and statistical rules. Change the method slightly, and the apparent extent of a structure can change too. This does not mean the structure is fake. It means classification at cosmic scales can be subtle. Imagine asking where a mountain range ends. Depending on contour lines, elevation cutoffs, or geological criteria, answers vary. Yet the mountains remain real. Likewise, giant walls can be real patterns with fuzzy boundaries. Now, why does this matter emotionally? Because many people hear science was wrong. That is usually the least accurate interpretation. Science expects to be refined. When a surprising observation appears, the system is working exactly as intended. Predictions meet reality. Reality answers back. Models improve. No embarrassment required. If anything, uneventful agreement all the time would be less exciting. The Boss Great Wall and similar structures are valuable precisely because they force cosmologists to sharpen questions. What counts as homogeneity? At what scale does smoothing truly emerge? How rare are the rarest structures? How much clustering should dark matter produce under current models? Could observational bias exaggerate certain features? These are excellent questions, and excellent questions are among the best things science makes. Now let us consider probability. Even in ordinary life, rare things happen without violating rules. Someone wins a lottery, 100-year storm arrives. You meet two people in 1 week with the same oddly specific hobby, involving antique maps and competitive baking. Unlikely does not mean impossible. Given a vast enough universe, rare configurations may naturally occur somewhere. This is especially relevant because the observable universe contains an immense number of galaxies and regions. Large samples allow uncommon events to happen, so one giant wall may simply be an extreme tale of normal cosmic statistics. That possibility is not dramatic, but it is respectable. Another factor is perspective. We observe the universe from one location and through incomplete data sets, though increasingly rich ones. Survey boundaries, selection effects, redshift distortions, and measurement limits can influence how structures appear. As maps improve, some features become clearer, others less dramatic, others newly visible. Science is not a single snapshot. It is an evolving atlas. Now let us bring in dark energy briefly, because it influences the large-scale story. Dark energy appears to drive accelerated cosmic expansion. Over time, this expansion tends to suppress growth of structure on very large scales by pulling distant regions apart faster. That means the universe is not infinitely generous with time for clustering. Structures had a window in which gravity could build before accelerated expansion increasingly diluted future opportunities. This is one reason very large connected patterns attract attention. They reflect the interplay of early seeds, gravity's persistence, and expansion's resistance. The cosmos built while the clock was running. There is something quietly dramatic in that. Now, perhaps the most comforting point of all, surprise is not failure. If a structure seems larger than expected, it does not mean physics has collapsed. It means understanding has room to grow. Many of humanity's greatest advances began as mismatches between theory and observation. Mercury's orbit helped lead toward relativity. Unexpected spectral lines helped shape quantum theory. The accelerating universe itself was a surprise. Nature often teaches by refusing to behave too neatly. The Boss Great Wall may not require revolutionary new physics. It may fit comfortably within refined statistics and careful definitions. But even if so, it still serves an important role. It reminds us not to confuse simplified models with finished truth. The map is good. Reality is larger. That principle extends beyond cosmology. We build frameworks to navigate life too. Schedules, plans, assumptions, identities. Useful things, all of them. Yet reality occasionally presents a giant wall of galaxies where we expected smooth averages. Then we adapt. If giant structures challenge our sense of what the universe should look like, what exactly was the original expectation of smoothness? And why did scientists trust it so much in the first place? There are few ideas in science more useful than a good simplifying assumption. Without them, progress would be painfully slow. Every problem would begin with endless complexity. Every equation would drag in the full chaos of reality, and every researcher would eventually wander outside for fresh air and reconsider their career choices. A simplifying assumption does not claim the world is perfectly simple. It says, for the purpose of understanding something deeper, let us begin with a cleaner version and test how far it works. The cosmological principle is one of the grandest such assumptions ever made. In gentle terms, it says that on sufficiently large scales, the universe is roughly the same everywhere and in every direction. Not identical in every local detail, of course. That would be absurd. Stars exist in some places and not others. Galaxies cluster. Voids open. Black holes lurk. Somewhere right now, a moon circles a planet no one has named. But if you zoom out far enough, the messiness should average away. The universe, statistically speaking, was supposed to become smooth. That phrase can sound almost philosophical, but it emerged from practical need. If cosmologists had to model a universe where every region was fundamentally unique and every direction obeyed different rules, the mathematics would become far more difficult. Predictive power would shrink. Elegant equations would retire early. Instead, assuming large-scale uniformity allowed, researchers to describe cosmic expansion, matter density, curvature, and history using tractable models, and remarkably it worked. That success is important. The cosmological principle was not chosen because scientists enjoy tidy thoughts more than anyone else. It was adopted because observations strongly suggested it was useful and approximately true. When astronomers look in different directions across the sky, the large-scale universe appears broadly similar. No obvious centre announces itself. No special edge appears. Galaxies exist in all directions. Cosmic microwave background radiation, the afterglow of the early universe, is astonishingly uniform with only tiny fluctuations. This supported a profound idea. Perhaps the universe has no privileged location. Perhaps our place is not special. Astronomy has taught versions of this lesson repeatedly. Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. The Milky Way is not the centre of the universe. The cosmological principle extends that humility mathematically. Wherever you are, on the largest scales, the universe should look much the same. That is both sobering and strangely comforting. Now, let us clarify two key words. Homogeneous means roughly uniform in composition when averaged over large enough distances. Matter density should not wildly differ from region to region once enough space is included. Isotropic means roughly the same in every direction. Look north, south, east, west, or the cosmic equivalent of directions that no longer help, and the large-scale view should statistically resemble itself. You can have one without the other in some mathematical scenarios, but modern cosmology generally uses both together in standard models. These assumptions lead naturally to the Friedmann-Lemaitre-Robertson-Walker metric, one of the foundational descriptions of an expanding universe in general relativity. A formidable name, but a useful framework. It allows the cosmos to expand uniformly without needing one central explosion point in space. That last misunderstanding is common. The Big Bang was not matter exploding outward into pre-existing emptiness from one location. It was space itself expanding everywhere. If the universe is homogeneous and isotropic, expansion can happen uniformly without a centre inside the system. Like raisins separating in rising dough, every raisin sees others moving away. though unlike raisins, galaxies rarely improve pastries. Now, why was the universe supposed to be smooth? Because if early matter was nearly uniform, and if cosmic expansion operates broadly the same everywhere, then beyond certain scales, local clumps should blur into averages. Think of weather. Stand outside and conditions vary wildly by hour. Wind gusts, clouds, rain, sun, temperature swings. But climate averages across years reveal broader patterns. Likewise, galaxies may cluster locally, but across immense distances the universe should settle into statistical regularity. That expectation guided decades of cosmology. Then came ever better surveys. As maps improved, astronomers saw the cosmic web more clearly. Galaxies formed clusters, filaments, walls, and voids. Structures like the Sloan Great Wall and the Boss Great Wall raised an interesting tension. If smoothing occurs, how large can these irregular patterns remain before the assumption becomes uncomfortable? This is not a fatal contradiction, it is a scale question. The cosmological principle does not say the universe must look smooth at every distance. It says smoothness should emerge when averaged over sufficiently large volumes. So scientists ask, what counts as sufficiently large? 100 million light-years? 300 million? A billion? More? That threshold is still studied using observational statistics and simulations. This is where headlines often oversimplify. Huge wall breaks cosmology sounds dramatic. In reality, the conversation is subtler. If giant structures exist but remain consistent with expected statistical fluctuations and averaging scales, then cosmology survives comfortably. If not, then refinements may be needed. Either way, science advances. Now let us appreciate how bold the original principle really was. From one planet around one star in one galaxy, humans inferred that no location is fundamentally special and that the universe behaves similarly elsewhere. That is an astonishing leap, and yet evidence has repeatedly rewarded it. The cosmic microwave background is nearly uniform across the sky to extraordinary precision. Galaxies on the broadest scales do tend towards statistical regularity. Expansion appears universal rather than directional. Still, the universe enjoys adding texture to our confidence. Those tiny early fluctuations in the microwave background, only slight temperature variations, were enough to seed all later structure. Smoothness was never perfection. It always contained wrinkles, and wrinkles, given gravity and time, become galaxies. That image is worth keeping. The universe began nearly smooth, not featureless. Subtle differences mattered. They still do. Now consider daily life. We often mistake averages for lived reality. Average temperature says little about today's breeze. Average traffic says little about your commute. Average wealth says little about a household. Average mood says little about a person this evening. Likewise, a statistically smooth universe can still contain dramatic local complexity. The cosmological principle is about averages, not scenery. That distinction prevents much confusion. There is also philosophical elegance here. A universe with no preferred centre is democratic in a cosmic sense. No throne room, no front row, no privileged balcony seat from which reality makes special announcements. Any observer anywhere, given sufficient tools, should uncover the same broad laws. That idea sits beautifully with science itself. Truth should not depend on postcode. Now let us be fair to the principle's critics and testers. Some researchers investigate whether large-scale anomalies, alignments, unusual flows, or unexpectedly giant structures hint at departures from perfect homogeneity or isotropy. Most such claims require careful scrutiny. Some fade with better data. Some remain intriguing. All are worth testing. This is healthy. Principles earn trust by surviving challenges, not by avoiding them. The cosmological principle has survived many, but it is still a principle, not sacred furniture. If stronger evidence someday demanded revision, cosmology would adapt. That flexibility is strength, not weakness. Now think again of the boss Great Wall. Its existence does not necessarily mean the universe is not smooth on large scales. It means we must define scales carefully, measure rigorously, and remember that smoothness can coexist with giant local structures. A beach may look smooth from afar while containing dunes. An ocean may look level while holding waves. A universe may average evenly while containing walls of galaxies. Reality often contains both pattern and exception. There is something reassuring in that balance. We do not need perfection for order. We need tendencies. If the universe was nearly smooth in the beginning, how did tiny wrinkles grow into giant walls, clusters and webs at all? What process turned faint early irregularities into the grand structures we now map across the sky? Long before the boss Great Wall arrived to unsettle intuitions and inspire dramatic headlines, astronomers had already encountered a recurring theme of modern cosmology. Every time we think we have a comfortable sense of scale, the universe produces something larger. It does this with almost comic consistency. We learn the size of Earth, then the Sun dwarfs it. We learn the size of the solar system, then the galaxy overwhelms it. We learn the scale of the Milky Way, then neighbouring galaxies stretch the picture wider. We grow accustomed to galaxy clusters, then superclusters appear. And once superclusters begin to feel manageable, the cosmos calmly presents walls. The boss Great Wall belongs to a family of discoveries sometimes described as giant large-scale structures, immense arrangements of galaxies or high-energy sources that challenge the imagination and sharpen scientific questions. Among the most famous earlier examples are the Sloan Great Wall and the Hercules Corona Borealis Great Wall Candidate. Their names sound like landmarks in a mythic atlas. In truth, they are products of surveys, statistics, and patient mapping. Let us begin with the Sloan Great Wall. Discovered in 2003 using data from the Sloan Digital Sky Survey, the Sloan Great Wall was one of the first truly jaw-dropping demonstrations that the universe contains coherent structures on scales larger than many had comfortably internalized. The Sloan Digital Sky Survey, or SDSS, was transformative because it did not merely observe isolated objects. It systematically mapped vast numbers of galaxies, producing a rich three-dimensional picture of cosmic distribution. And once enough dots are plotted, patterns start behaving boldly. Within that growing map, researchers identified an enormous wall-like arrangement of galaxies spanning roughly 1.3 to 1.4 billion light-years in length, depending on how measured and defined. That number deserves the respectful silence all billion light-year figures deserve. At the time, it was among the largest known structures in the universe. It extended far beyond scales that once felt intuitively large enough for clustering. The Sloan Great Wall was not a brick barrier drifting through darkness. Like the boss Great Wall, it was a connected concentration of galaxy clusters, filaments, and superclusters appearing wall-like in large-scale maps. Its importance was twofold. First, it showed that cosmic structure could remain coherent over astonishing distances. Second, it raised questions about how such structures fit within expectations of large-scale homogeneity. Scientists did not panic. They did what scientists often do when reality becomes interesting. They gathered more data. Now, the Sloan Great Wall also taught an important lesson about naming. Once you call one thing a Great Wall, future large structures become difficult to title modestly. There is only so much grandeur available in language before names begin sounding like luxury apartment complexes or fantasy battlefields. Still, the names endure because they communicate emotional truth. These structures are immense. Now let us turn to the Hercules Corona Borealis Great Wall, perhaps the most controversial and headline-friendly of the group. This candidate structure emerged from studies of gamma-ray bursts, some of the most energetic explosions known in the universe. Gamma-ray bursts are brief flashes of intense gamma radiation, often linked to catastrophic stellar events such as collapsing massive stars or mergers involving compact objects. They are visible across vast cosmic distances, making them useful probes of the distant universe. Useful, though not simple. Researchers noticed an apparent clustering of gamma-ray bursts in the direction of the constellations Hercules and Corona Borealis, suggesting an enormous large-scale concentration that, if interpreted as one coherent structure, could span on the order of 10 billion light-years. Yes, billion with a 10 in front of it. At that size, many people stop imagining entirely and simply nod politely. Now, caution is especially important here. Unlike galaxy redshift walls mapped through dense surveys of galaxy positions, the Hercules Corona Borealis Great Wall is based on statistical clustering of gamma-ray bursts, which are rarer events and sampled differently. That makes interpretation more challenging. Is it truly one connected structure? Is it an artifact of sparse data and selection effects? Is it a temporary statistical signal awaiting stronger confirmation or revision? These remain active concerns, so while the name became famous, many cosmologists treat it carefully as they should. Science is most trustworthy when excitement and skepticism travel together. Still, whether or not the full dramatic interpretation holds, the episode highlights something valuable. Our maps of the universe continue to improve, and with every new method we sometimes glimpse patterns that force deeper scrutiny. Now compare these earlier giants with the Boss Great Wall. The Sloan Great Wall emerged from galaxy survey mapping. The Boss Great Wall also emerged from sophisticated galaxy survey data, with improved reach and statistical tools. The Hercules Corona Borealis candidate arose through gamma-ray burst distributions, different methods, different strengths, different uncertainties. Yet all three point toward the same central theme. The universe possesses structure on scales far beyond ordinary expectation. That phrase does not necessarily mean standard cosmology is broken. It means the universe contains rich texture, and our intuition is a poor measuring instrument. We should not ask intuition to referee billion light-year geometry. It was designed for stairs and weather. Now let us talk about why these discoveries arrive in sequence rather than all at once. Partly it is technology. Earlier astronomers lacked modern digital surveys, giant databases, precision spectroscopy, automated pattern analysis, and computers willing to sort millions of objects without complaining. As instruments improved, the visible universe expanded in detail. It is much like mapping Earth. A village map reveals streets, a regional map reveals rivers, a continental map reveals mountain chains, a satellite map reveals weather systems. Each scale depends on tools. Likewise, the Sloan Great Wall could only be found once surveys reached sufficient scope. The Boss Great Wall required later, deeper data. Future surveys may reveal still more subtle or larger structures. This is worth remembering whenever science discovers something new. Often, reality was there all along. We merely improved our eyesight. Now there is also a statistical reason giant structures keep appearing. If you sample larger cosmic volumes, you gain access to rarer extremes. In a small patch of forest, you may not find the tallest tree. In a vast forest, extraordinary trees become more likely somewhere. Likewise, as surveys cover larger portions of the universe, unusual structures become more likely to be noticed. That does not make them impossible. It makes them part of a larger sample. This principle can feel less dramatic than physics overturned, but it is often more accurate. Now there is something psychologically fascinating about names like Sloan Great Wall and Boss Great Wall. They borrow from human architecture because architecture is how we understand order at scale. Walls, webs, clusters, filaments, sheets. We use earthly language to describe cosmic patterns. That is not weakness, it is translation. The universe does not speak English. We do. So we borrow words sturdy enough to carry partial meaning. Now imagine standing inside one of these structures. You would not feel inside a wall. You would inhabit one galaxy among many. Local stars would shine. Nearby space would still be mostly emptiness. The grand pattern only emerges when seen through maps and data from immense perspective. This is true of many systems. No ant sees the full colony. No driver sees the whole traffic network. No individual year sees the climate trend. Large truths often require distance. That may be one reason astronomy feels humbling. It repeatedly reminds us that local experience is real but incomplete. Now let us address the emotional side. Hearing about giant cosmic walls can trigger two opposite responses. One is insignificance. We are tiny. The other is belonging. We are part of something astonishingly large. Both responses are understandable, but I would gently favour the second. Tiny things can belong to grand realities without being diminished by them. A note in a symphony is small. It still matters. Now, what did these earlier giants really accomplish scientifically? They forced cosmologists to refine expectations about clustering scales, connectivity, statistical rarity, and the meaning of large-scale smoothness. They also demonstrated the power of survey astronomy, and perhaps most importantly, they taught humility. Whenever we think the map is nearly finished, another contour appears. Another question naturally follows. If giant structures keep being found, are we uncovering genuine limits of our models, or are we simply learning that the universe is more textured, more lumpy, and more complicated than our earliest clean assumptions allowed? Are we missing something fundamental? It is an excellent question, but also a dangerous one if handled carelessly. Used wisely, it opens doors. Used recklessly, it invites every unsupported idea wearing a dramatic coat. So tonight, let us handle it properly. When structures like the Boss Great Wall seem larger, rarer, or more coherent than expected, it is natural to wonder whether our current picture of the universe is incomplete at a deep level. Perhaps some hidden ingredient remains undiscovered. Perhaps one of our assumptions needs revision. Perhaps we are looking at evidence that the cosmos is stranger than standard models allow. Or perhaps we are simply witnessing the normal process of science, where difficult observations sharpen good theories rather than destroy them. Both possibilities deserve calm attention. Now, the standard model of cosmology, often called lambda CDM, has been extraordinarily successful. The lambda refers to dark energy, associated with accelerated cosmic expansion. CDM stands for cold dark matter, matter that moves relatively slowly compared with the light and helps structure form gravitationally. This framework explains a great deal. It accounts for the cosmic microwave background with remarkable precision. It describes the large-scale expansion of space. It models galaxy clustering statistically. It supports simulations that reproduce web-like cosmic structure. It has become standard not through popularity contests, but because it works well. That matters. One surprising structure does not casually overturn a model supported by many lines of evidence. Science is not a tower balanced on one observation. It is more like a bridge held by many supports. Still, even strong models can be incomplete. Newtonian gravity worked beautifully for centuries, then relativity refined it. Classical physics described much, then quantum theory revealed deeper layers. Good theories often survive by becoming special cases of broader ones. So asking whether something fundamental is missing is not rebellion against science, it is part of science. Now let us consider what missing something fundamental could realistically mean. It might mean our understanding of dark matter is incomplete. Dark matter is inferred through gravity, but its precise nature remains unknown. We know how it behaves broadly in cosmological models, yet we do not know exactly what particle or mechanism underlies it. If dark matter has interactions or properties beyond current assumptions, structure formation could be affected. Perhaps clustering happens differently. Perhaps filament growth changes subtly. Perhaps rare large connected structures become more common than expected. This is a legitimate avenue of research. It might also mean dark energy is more complicated than a simple constant. If cosmic acceleration has evolved over time differently than assumed, that could alter growth rates of large-scale structure across billions of years. Again, possible. Not proven, but possible. Another option is gravity itself. General relativity has passed many tests brilliantly, yet most direct tests occur on solar system, stellar or galactic scales, rather than the largest cosmological scales. Some researchers explore modified gravity models that reproduce observed expansion or clustering differently. This is difficult work, because any new model must match many successful predictions already made by existing theory. Changing gravity is easy in conversation. Making it consistent with data is much harder. Then there is the possibility that nothing fundamental is missing at all. That answer is often less glamorous, but frequently correct. Maybe giant structures are rare, but expected statistical outcomes in a sufficiently large universe. Maybe our intuitions about too large are simply poor guides. Maybe structure-finding algorithms connect regions in ways that feel dramatic, but remain fully compatible with current cosmology. Maybe survey limitations temporarily exaggerate coherence. Science must always keep this possibility on the table. Sometimes mystery is not hidden physics, sometimes it is hidden bookkeeping. Now let us talk about assumptions, because many fundamental questions turn out to be questions about assumptions rather than laws. Suppose you assume homogeneity emerges by a certain scale. Then observations suggest larger persistent structure. Perhaps the issue is not the existence of walls, but your smoothing scale. Suppose you assume structures should be counted one way. A new method groups galaxies differently. The problem may partly be classification. Suppose you assume your data sample is representative. Later surveys reveal bias. Again, not new physics, new humility. This happens often in science and in life. We sometimes frame surprises as failures of reality, when they are really failures of framing. Now there is another subtle possibility. We may be missing something not in equations but in measurement depth. The observable universe is immense, but our maps remain incomplete. Future surveys such as larger spectroscopic campaigns, deeper sky catalogues, better weak lensing maps, and next-generation telescopes will reveal far more structure. It is entirely possible that what now appears extraordinary will later appear ordinary within a richer census. The tallest visible tree often changes when more forest is explored. That is a wonderfully common scientific outcome. Now let us be honest about human psychology. We're drawn to phrases like, "Science can't explain this," because they promise drama. Yet science usually advances more quietly, not with collapse, but with refinement, not with total replacement, but parameter adjustments, improved data, stronger simulations, better uncertainty estimates, revised thresholds, and occasional embarrassment for overconfident headlines. The Boss Great Wall may one day be remembered not as the structure that shattered cosmology, but as one of many observations that helped tune our understanding of large-scale clustering. That would still be significant. Incremental progress built most of modern civilization. Now, if something fundamental were missing, how would we know? Not from one surprising wall alone. We would look for consistent patterns across multiple independent observations. Do galaxy surveys repeatedly disagree with simulations? Do lensing maps imply different matter behavior? Do cosmic microwave background measurements conflict with later structure growth? Do expansion histories disagree across methods? Do multiple anomalies point in one direction? When independent tensions align, confidence grows that deeper revision may be needed. This is why modern cosmology pays close attention to tensions between datasets, not just isolated curiosities. Science trusts repeated whispers more than single shouts. Now let us widen the lens. The phrase, "missing something fundamental," also reflects a healthy philosophical stance. It acknowledges that even our best models are maps, not reality itself. Maps can be excellent. They can guide ships, airplanes, surgery, and spacecraft. but maps are always selective. No map contains every grain of sand or gust of wind. Likewise, cosmological models capture essential patterns while omitting detail not needed for their purpose. Sometimes omitted detail matters later, then the map improves. This is normal. Now perhaps there is comfort here. You do not need the final theory of everything for the night sky to be beautiful. Scientists do not need perfect knowledge for discovery to continue. Unfinished understanding is not failure. It is the natural condition of inquiry. The universe remains generous enough to be knowable in part and mysterious in part. That balance may be ideal. Complete chaos would teach nothing. Complete transparency would leave little to seek. Instead, reality offers solvable puzzles wrapped in larger puzzles. Now return for a moment to the Boss Great Wall. It stands, whether fully ordinary or mildly provocative, as a reminder that scale can still surprise experts. That alone is valuable. A living science should be surprised sometimes. If every observation merely confirmed expectation, curiosity would become clerical work. Now, are we missing something fundamental? Possibly. Possibly not. At present, the honest answer is measured uncertainty. Our current models explain much and remain powerful. Some observations continue to test their edges. Future data will decide whether those edges need sanding or rebuilding. That is a strong position, not a weak one. Certainty is comfortable, evidence is better. If nothing fundamental is broken, could it simply be that the universe is less perfectly smooth, less evenly distributed, and more textured than our earliest clean assumptions first suggested? There is a quiet difference between saying a theory is wrong and saying reality is messier than our first description of it. Those two ideas are often confused. The first suggests collapse, replacement, overturned foundations, dramatic music, and headlines written with suspicious enthusiasm. The second suggests refinement, and refinement is how science usually moves. So when we ask whether the universe might be less uniform than we thought, we're not necessarily asking whether modern cosmology has failed. We're asking whether the large-scale texture of reality may contain more variation, more structure, or more subtle unevenness than our earlier simplified assumptions captured. That is a gentler question. It is also a very important one. The standard cosmological picture assumes that on sufficiently large scales, matter distribution becomes statistically smooth. This assumption has worked well. It helps explain cosmic expansion, supports powerful mathematical models, and agrees with many observations. But smooth enough is not the same as perfectly uniform, and large enough is not a fixed emotional category. It must be measured. This is where discoveries like giant walls, extensive filaments, vast voids, and clustering anomalies become interesting. They push us to ask where smoothness truly emerges, how strong fluctuations remain at extreme scales, and whether our expectations about cosmic averaging were too optimistic. Now imagine standing on Earth. From ground level, terrain is irregular. Hills, valleys, trees, streets, fences, rivers, buildings, and that one curb designed by a personal enemy of ankles. Rise high enough, and the land appears smoother. Rise farther still, and continents look cleaner in outline. Yet even from orbit, mountains remain mountains, trenches remain trenches, weather systems swirl, ice sheets gleam, deserts spread, forests darken the surface. Smoothness depends on scale and purpose. The same may be true of the universe. At one scale, galaxies are obvious clumps. At another, clusters and filaments dominate. At another, perhaps the whole thing averages beautifully. The real question is where one regime becomes the next. Now, some observational studies have explored whether the transition to homogeneity occurs at scales larger than once assumed. Others find broad agreement with standard expectations. Different methods, datasets, and definitions can yield different estimates. That sentence may sound modest, but it is exactly how frontier science often looks. Not clean certainty, measured debate. Some analyses use galaxy counts within expanding spheres. If matter becomes homogeneous, counts should stabilize statistically in expected ways as scales grow. Others examine fractal dimensions, clustering functions, void statistics, or correlations in large surveys. These methods ask a shared question. Does the universe smooth out as predicted, and if so, when? So far, mainstream evidence generally supports large-scale homogeneity, but discussions continue over details, scales, and anomalies. That is a healthy place for science to be. Now let us address the word uniform. Uniformity in cosmology is statistical, not visual. No one expects every cubic region of space to contain identical numbers of galaxies, like neatly packed storage bins. The universe is not a warehouse. Instead, uniformity means that when you average over sufficiently large regions, the variations become small relative to the whole. This distinction matters because many public misunderstandings arise from imagining scientists promised a featureless cosmos. They did not. They predicted structured local complexity embedded within broad, large-scale regularity. Those are compatible ideas. A loaf of bread may contain bubbles and texture while still being bread throughout. An ocean may contain waves while remaining one sea. A universe may contain giant walls while still averaging smooth over larger domains. Now, could the universe be somewhat less uniform than idealized models suggest? Certainly in the practical sense that all models simplify. The real universe contains survey limitations, evolving structures, nonlinear growth, bias in how luminous galaxies trace matter, and subtle statistical features that tidy textbook sketches omit. But could it be fundamentally less uniform in a way requiring deeper revision? That is the sharper question. Some researchers have explored large-scale anisotropies, preferred directions, unusual flows of galaxy clusters, asymmetries in cosmic microwave background data, or clustering tensions. Most such claims face serious scrutiny, and many weaken with improved measurements or better handling of systematics. Still, it is wise to investigate them. A principle gains strength by surviving tests. Now let us talk about voids, because emptiness can mimic non-uniformity in interesting ways. If you live near the edge of a large underdense region, local expansion measurements and galaxy distributions might look slightly different than average expectations. Likewise, dense regions can bias local impressions. We observe the universe from one location, not from nowhere. That sentence should remain pinned above many scientific desks. Perspective matters, selection matters, context matters. This does not invalidate observations. It simply reminds us that interpretation requires care. Now, another subtle point concerns dark matter and visible matter. Galaxies are what we most easily map, but galaxies are biased tracers of total matter. They form preferentially in denser environments and reflect complicated astrophysical histories. So visible galaxy distribution is not a perfect one-to-one photograph of all matter. This means apparent non-uniformity in luminous structure does not automatically imply equivalent non-uniformity in total mass distribution. Again, nuance matters. The universe rarely rewards shortcuts. Now let us step back emotionally for a moment. Why does this question attract so much interest? Because uniformity carries philosophical weight. A largely uniform universe suggests no privileged regions, no cosmic center, no specially favored direction. It supports the idea that the laws of nature operate broadly the same everywhere. That is elegant. But a less uniform universe would not automatically become chaotic or mystical. It would simply be more textured, more contingent, more detailed than our first clean summary. And perhaps we should not fear that possibility. Many things become richer when detail is admitted. Maps improve when terrain returns. Music improves when variation returns. Stories improve when characters stop being symbols and become people. Perhaps cosmology too grows richer when the neatest simplifications meet measured complexity. Now it is worth emphasizing that current evidence still strongly favors the broad success of standard large-scale cosmology. We are not on the brink of discovering the universe is secretly arranged like a giant spiral staircase, or spelling messages in galaxy clusters. The likely reality is subtler. The universe may be statistically smooth overall, while containing more interesting intermediate-scale structure than early intuition appreciated. That is not revolution, it is maturity. Young sciences often begin with broad strokes. Mature sciences learn texture. Now think of weather forecasts. Early understanding might say, air moves and temperatures vary. Better understanding adds fronts, pressure systems, ocean cycles, local topography, seasonal oscillations, humidity feedbacks, microclimates. The basic picture survives, the detail deepens. Cosmology may be in a similar phase regarding structure. Now there is also a practical humility here. We have mapped only part of the observable universe in high detail. Future surveys from next-generation telescopes and missions will chart many more galaxies, better lensing maps, deeper redshift catalogues, and improved cosmic history. As maps improve, our sense of uniformity will become more precise. Some apparent anomalies may fade, others may sharpen. Either outcome is valuable. Reality does not owe us simplicity, only consistency. Now perhaps the most soothing conclusion is this. Uniformity and wonder are not opposites. A smooth average universe can still contain spectacular walls, clusters, black holes, stars, planets, oceans, forests, cities, and tonight's quiet room. Likewise, a textured universe need not threaten understanding. It simply asks for better maps. If our maps depend on distant light and perspective, how much of what we call structure is shaped not only by what is out there, but by the limits of how and when we are able to observe it at all? Look out through a window at night, and it can feel as though sight is immediate. You glance at a street lamp and there it is. You look at the moon, and there it is. You notice a star between clouds and there it is too, quiet and punctual. Vision feels instantaneous, clean, uncomplicated. We see things where they are, when they are. The universe, with typical confidence, disagrees. When astronomers observe space, they are not seeing objects as they exist right now in some universal present. They are seeing messages carried by light, and every message takes time to arrive. That simple fact changes everything. It means every telescope is also a time machine, though a disappointingly one-directional one. It can look back, never forward. It can receive ancient news, but cannot skip ahead to tomorrow's weather on Neptune. And when we discuss giant structures like the Boss Great Wall, this becomes especially important. Because the wall is not merely far away, it is old in the act of being seen. To understand the limits of observation, let us begin with something familiar. Sunlight takes about 8 minutes to reach Earth. So when you look at the sun, you are seeing it as it was 8 minutes ago. If the sun changed dramatically, we would continue admiring its old version for several minutes before receiving the update. The moon is closer. Its light reaches us in about 1.3 seconds. Jupiter, depending on orbital positions, may be tens of minutes delayed. Nearby stars are years delayed. Distant galaxies are millions or billions of years delayed. This means astronomy is not the study of objects alone. It is the study of delayed appearances. Now imagine the Boss Great Wall. The galaxies composing that immense structure lie at cosmological distances. Their light began travelling toward us long before modern human history, long before agriculture in some cases for nearer examples, and far longer for more distant regions. We map them not in their current state, whatever current means across cosmic distance, but in past states corresponding to when their light departed. So when astronomers chart the universe, they are not drawing one synchronized portrait. They are assembling a layered archive. Some regions are seen as they were more recently. More distant regions are seen deeper in the past. The farther outward we look, the earlier the chapter. This creates a subtle challenge that many people never have reason to consider. When you look across a room, all parts of the room are effectively present together for practical purposes. Light travel time across a room is negligible. Even across continents, everyday communication feels immediate enough that we casually forget the delay. Cosmology cannot afford that casualness. Across billions of light years, delay is the whole story. Suppose two galaxies appear near one another in a survey map but lie at different distances. You may be seeing one from a later era than the other. Their apparent proximity in space can involve different slices of time. This is why large-scale maps require careful interpretation. Astronomers convert redshift, brightness, spectra, and cosmological models into distance estimates, then reconstruct positions in an expanding universe. They're not merely pointing and labeling, they're translating ancient light into geometry. That process is remarkable. It is also imperfect. Let us talk about imperfection kindly, because science depends on understanding limits without despairing over them. One limit is brightness. Distant objects grow faint. Light spreads out. Surface brightness declines. Small galaxies that might be visible nearby become difficult or impossible to detect at great distances. Surveys therefore miss some objects, especially dim ones. This creates selection effects. If you only detect brighter galaxies in distant regions, your map is incomplete in specific ways. Scientists account for this statistically, but it remains part of the observational challenge. Another limit is dust. Dust within galaxies, between stars, and within our own Milky Way can obscure light, redden signals, and complicate measurements. Space looks clean from postcards, but the universe contains an impressive amount of drifting particulate ambition. Then there is instrumentation. Telescopes have finite sensitivity. Spectrographs have resolution limits. Observing time is precious. Weather affects ground-based observatories. Atmospheres blur images. Detectors must be calibrated. Software must behave, which is never guaranteed. Even with advanced tools, every observation is filtered through constraints. Now add motion. Galaxies do not simply sit, still while space expands politely around them. They also possess local motions due to gravity. These peculiar velocities can distort redshift measurements used to infer distance. In galaxy surveys, this produces effects with memorable names such as the Finger of God, where clusters appear elongated along the line of sight because member galaxies move relative to one another. Astronomy occasionally sounds like a discipline that secretly enjoys dramatic titles. These distortions must be modelled carefully when reconstructing large-scale structure. Otherwise, patterns can be misread. Now let us consider the phrase "seeing through time." It is accurate in more than one sense. When we observe distant galaxies, we are seeing earlier evolutionary stages. Young galaxies may be more chaotic. Star formation rates differ. Merger histories differ. Chemical abundances differ. Black holes may be feeding more actively. So distance gives not only space, but history. The deeper we look, the younger the universe appears. That means the Boss Great Wall and similar structures are not just spatial discoveries. They are evidence about how matter was arranged in earlier cosmic eras. We study structure formation by comparing different distances, which is really comparing different times. Nearby regions show later outcomes. Farther regions reveal earlier development. The universe leaves us a timeline written in light. Now there is something beautifully strange here. Most sciences examine the present and infer the past. Astronomy often observes the past directly and infers the present. You cannot see dinosaurs in their own time. You can, however, see ancient galaxies as they were billions of years ago. That is an extraordinary privilege of physics, yet it comes with limits. There is a horizon to what we can observe. Because the universe has a finite age and light travels at finite speed, there exists an observable universe, the region from which light has had time to reach us since the hot early stages of cosmic history. Beyond that horizon may lie more galaxies, more walls, more voids, perhaps endless continuation, but light from there has not reached us and may never do so depending on cosmic expansion. So our cosmic map, however grand, is partial by principle, not incomplete because of laziness, incomplete because causality has boundaries. This is a humbling fact. The observable universe is vast beyond comprehension, yet it may still be only a portion of what exists. Maps always have edges somewhere. Now think again about giant structures. When headlines claim largest known structure, the phrase contains two cautionary words, known and structure. Known means within available data and methods. Structure means defined according to criteria that can evolve. Future surveys may discover larger or differently connected systems. Some current candidates may be reclassified. Boundaries may shift. This does not weaken discovery. It is how exploration works. Early world maps change coastlines often. Cosmic maps do too. Now let us step into the emotional side of these limits. Some people find observational boundaries frustrating. They want certainty, complete knowledge, final answers, understandable desires. But limits also create wonder. A universe fully exhausted by 1 century of measurement would be a smaller place intellectually than the one we inhabit now. Instead, reality remains generous enough to reveal much and withhold much. We know enough to map walls of galaxies. We do not know everything beyond the horizon. That balance keeps curiosity alive. There is also comfort in remembering that all knowledge is situated. You know your room better than the deep ocean. A botanist knows leaves better than quasars. A baker may know dough better than dark energy. Astronomers know the universe through light and mathematics, which are powerful but not infinite tools. Every perspective has strengths and limits. This need not be discouraging. It can make knowledge gentler. Now imagine the Boss Great Wall once more. We do not see it as a tourist sees a canyon. We know it through redshifts, catalogues, clustering statistics, surveys, and reconstructed three-dimensional maps built from delayed photons crossing unimaginable time. That is not lesser seeing. It is different seeing. Human eyesight alone could never reveal such truths, but human minds extended by instruments can, and perhaps that is one of the most reassuring lessons in science. We are small creatures with limited senses, yet not trapped by them. We build methods. We correct bias. We stretch perception beyond biology. We learn to see what naked eyes cannot. If observation is always local and delayed, what does our own place inside this immense cosmic network really mean when we finally zoom outward far enough to include ourselves in the map? Begin, for a moment, with the smallest version of your evening. Perhaps you're sitting in a chair, perhaps lying in bed. Perhaps one foot is warmer than the other for reasons no science has fully resolved. Maybe there is a lamp nearby, a window, a faint sound outside, the soft weight of blankets, the memory of today still unpacking itself in the background. From this scale, life is intimate. A room matters, a message matters, a plan for tomorrow matters. Whether you remember to charge something matters more than any galaxy ever has. This is normal. Human life is lived locally. Yet one of astronomy's gentlest powers is the ability to widen the frame without erasing the close-up view. It does not ask you to abandon the room. It simply invites you to place the room somewhere larger. So let us zoom out carefully. You are on Earth, a rocky planet orbiting the Sun once every year. Earth rotates once roughly every 24 hours, giving us mornings, afternoons, late nights, and the occasional 3 a.m. moment when a minor memory suddenly feels legally significant. Earth is one of several major planets in the solar system. That system extends far beyond the visible planets into belts of icy bodies, scattered objects, and a gravitational influence stretching into deep, cold distances. Zoom out farther. The solar system is one tiny part of the Milky Way, a spiral galaxy containing hundreds of billions of stars. Our sun is not central, Not unusual, and not commanding special attention from galactic management. It resides in one region among many, orbiting the galactic centre over hundreds of millions of years. Already, scale begins to soften ordinary intuition. Yet the Milky Way itself is not alone. Nearby lies Andromeda Galaxy, along with smaller companions and neighbours. Together these form the local group, a modest gathering of galaxies bound by gravity. Zoom outward again. The local group belongs to larger associations and neighbouring concentrations of galaxies, linked through filaments and clusters within the cosmic web. Matter gathers in networks, not isolated islands. Galaxies participate in larger geography. Continue outward still. Now the Milky Way becomes one dot among many. The local group becomes a tiny marker. Entire clusters shrink into points. Walls, filaments and voids emerge. And somewhere in this grand map lies the kind of structure we have been discussing. The Boss Great Wall, a vast connected arrangement of galaxies and superclusters stretching across distances so large that words must work overtime just to keep up. At this scale, your galaxy is no longer the main character. Neither is mine. Neither is any single star. Patterns become the subject. That shift can feel unsettling at first. Many people hear cosmic perspective and translate it into insignificance. We are tiny. Yes, physically speaking, often true. But tiny is not the same as meaningless. A cell is tiny compared with a forest. A note is tiny compared with a symphony. A page is tiny compared with a library. Scale alone does not determine value. This is worth remembering. Now let us place you more specifically inside the structure of things. You are made of atoms forged through cosmic history. Hydrogen from the early universe. Heavier elements built in stars and scattered by stellar deaths long before Earth formed. The calcium in bones, iron in blood, oxygen you breathe, carbon in every living cell, all part of an ancient material cycle. So even before location, you belong chemically. You're not standing apart from the cosmos. You're one of its later arrangements. Then there is gravity. The same gravity helping shape giant walls and clusters also hold you to Earth, keeps oceans in place, guides planetary orbits, and organises galaxies. There is no separate set of elegant cosmic laws reserved only for glamorous distances. The ordinary and the immense share rules. This means your place in the universe is not merely geographic, it is participatory. You exist within the same physical story. Now imagine the map from far enough away. No one looking from 1 billion light years distant, if such a viewpoint were possible, would notice your street or city. They would not see national borders. They would not see deadlines. They would not know which email you regret sending. Those things vanish at scale. This can sound harsh until we notice what else vanishes. So do many anxieties. So do status games. So do temporary embarrassments. So does the idea that tonight's unfinished task defines your worth. Perspective removes some burdens along with some details. That is part of its kindness. Now, astronomy often gets accused of making humans feel small. I think that misses half the story. Yes, we are small in size, but we're also large in awareness. A patch of matter on one planet learned to model galaxy walls, infer dark matter, measure expansion, and ask reflective questions late at night. That is not small in any meaningful intellectual sense. The Boss Great Wall does not know you exist. You know it exists. There is a symmetry there, and it favours consciousness. Now let us talk about belonging without sentimentality. You do not need the universe to care personally about you for your existence to matter. Stars are not issuing evaluations. Superclusters are not ranking your productivity. Cosmic voids hold no grudges. Meaning is not handed down by galaxy walls. Meaning is made locally, in rooms, in relationships, in choices, in kindness, in persistence. The universe provides context, not instructions. That may be better. Now consider time. The Boss Great Wall spans light travel intervals beyond intuitive grasp. Human lives are brief by comparison. A single life may seem tiny against billions of years, yet brevity can intensify value. A sunset lasts minutes, music unfolds and ends, a conversation matters partly because it cannot be repeated exactly. Finite things often feel precious precisely because they are finite. So cosmic timescales do not diminish human time, they contrast with it. Contrast can sharpen appreciation. Now let us zoom in again, back through walls and filaments, back through clusters, back through local galaxies, back into the Milky Way, back to the solar system, back to Earth, back to your city, building, room, back to breathing. Notice what changed. The room did not become smaller because the universe became larger. It remained what it was. That is another useful lesson. Perspective need not erase intimacy. You can hold both scales at once. You can know about billion light-year structures and still care whether you sleep well tonight. You can understand dark matter statistics and still enjoy warm tea. You can accept cosmic vastness and still value one human evening. These are not contradictions, they are layers. Now there is something else to say about maps. When astronomers place us within cosmic structure, they do not assign destiny. They assign coordinates. Coordinates are modest things. They tell where, not why. Humans often ask maps to answer meaning questions they were never built to answer. Where am I? A map can help. What should I love? Different tool? How should I live? Different tool again. The universe can humble us, inspire us, steady us, but it does not replace the work of living. Now think of the Boss Great Wall once more. It is enormous, ancient in the light we receive, and composed of countless galaxies, each containing their own local realities. Somewhere within one galaxy, in one corner of a much larger network, beings could wonder about structures larger still. That possibility alone is comforting. Curiosity may not be unique to us. Even if it is still remarkable. Now perhaps the most peaceful conclusion is this. You do not need to be central to belong. You do not need to be large to matter. You do not need to understand everything to be honestly placed within it. You are here, on a world in motion, inside a galaxy among many, within a web of matter shaped over ages, aware enough to ask where you fit. That awareness is already a kind of home. Some of the most important discoveries in cosmology are made without anyone looking through a telescope at all. That sentence can sound suspicious at first. Astronomy surely is about observing the sky. Telescopes, domes, dramatic mountain locations, researchers wearing jackets against the cold, perhaps someone pointing upward with confidence. And yes, observation remains essential. But modern cosmology also studies the universe by building it again inside computers, not literally of course. No one has placed a functioning cosmos inside a server room and asked it to behave. What scientists create are simulations, mathematical universes governed by known physics, seeded with early conditions, then allowed to evolve over billions of years in accelerated digital time. These simulations have become one of our best tools for understanding whether structures like the Boss Great Wall are shocking, rare, expected, or merely rude to intuition. Because if we want to know whether something is too big to make sense, we need a standard of comparison. Reality alone gives us one sample. Simulations can give us many. Let us begin with the problem. We observe giant walls, filaments, clusters, and voids. Some structures seem so extensive that headlines quickly declare they should not exist. But nature does not publish its expectations in advance. To know what should happen, we must model what known physics predicts. So scientists start near the beginning. They take measurements of the early universe, especially tiny density fluctuations inferred from the cosmic microwave background. These fluctuations are small differences in matter distribution present when the universe was young. Then they feed those initial conditions into cosmological models. Dark matter is included. Ordinary matter is included. Expansion of space is included. Gravity is included, dark energy is included according to the model being tested. Then the system is evolved forward through time. Tiny denser regions pull in more matter. Filaments emerge, clusters form, voids widen, galaxies and halos develop statistically. The cosmic web appears. Watching this process in simulation is one of the great scientific pleasures of the modern age. What once looked like scattered numbers becomes flowing structure. And importantly, it often looks surprisingly like the real universe. That success is one reason the standard cosmological model remains so respected. Simulations built on it reproduce many observed large-scale patterns remarkably well. Now comes the key question. Do simulated universes produce structures comparable to the Boss Great Wall? The answer is subtle, which usually means honest. Sometimes yes, sometimes rarely, sometimes depending on definitions, sometimes structures that look similar in one metric differ in another. This is the nature of frontier science. Now let us talk about definitions because they matter more than they sound. Suppose you scatter cities across a continent and ask where one metropolitan region ends and another begins. If you connect nearby suburbs, roads, commuter zones, and adjacent towns, the resulting region may grow larger or smaller depending on your rules. The same applies to cosmic structures. How close must galaxy clusters be to count as connected? How dense must a filament be? What linking length is used in the algorithm? Do you merge neighbouring overdensities into one wall or count them separately? Change these choices, and the measured size of a structure can change significantly. So when simulations are asked whether impossible size walls exist, the first reply is often, please define wall, that is not evasion, it is rigor. Now, large simulation projects such as Millennium, Illustris, Bolshoi, Multidark, and many others have modelled cosmic structure formation across huge volumes. Each has different strengths, resolutions, and scientific goals, but together they provide a broad laboratory for testing expectations. Some focus on dark matter halos, some include detailed gas physics, some emphasize galaxy formation, some prioritize giant cosmic volumes to capture rare extremes. This last category matters especially for giant walls. Rare events require large samples. If you only simulate a small cosmic box, you may never produce the largest unusual structures simply because the sample is too limited. Expand the simulated volume, and rare giants become more likely somewhere. This principle is wonderfully ordinary. The tallest tree is easier to find in a vast forest than in a garden. Likewise, very large connected structures are easier to encounter in large simulated universes. Now, what have these comparisons generally shown? They suggest that while enormous structures can be uncommon, they are not automatically impossible under standard cosmology. Some may sit in the tail of the statistical distribution rather than outside it entirely. That distinction is crucial. Tail events feel shocking when encountered individually. But if the universe is large enough, tails get their turn. This happens in everyday life too. Someone wins an improbable contest. A storm breaks records. Two strangers discover identical birthdays in a crowded room. Rare does not mean forbidden. Now let us consider why intuition rebels. Human minds prefer moderate scales. We evolved among hills, weather, trees, and distances traversable on foot. A billion light-year wall feels absurd because our instincts have never calibrated for cosmic statistics. Simulations help by replacing instinct with counted outcomes. Instead of asking, "Does this feel too large?" scientists ask, "How often does this emerge under known assumptions?" That is a better question. Now there is another reason simulations are powerful. They reveal process, not just outcome. Observation gives snapshots from one real universe. Simulation lets researchers watch structure grow repeatedly. You can see matter stream along filaments. You can track halo mergers. You can measure how voids expand. You can test how changing dark matter properties alters clustering. You can ask what accelerated expansion suppresses. You can compare many cosmic histories. This turns cosmology from pure description into controlled experimentation, at least in model form, and that is transformative. Now, could simulations be wrong? Certainly. Every simulation depends on assumptions, numerical methods, finite resolution, and included physics. If dark matter behaves differently than modelled, if gravity changes subtly on huge scales, if baryonic feedback matters more than expected in some regime, outcomes can shift. Simulations are not reality. They are disciplined hypotheses made visible, but when many independent simulations under varying methods converge on similar broad structure, confidence grows. That convergence is scientifically valuable. Now let us return specifically to impossible size. Sometimes journalists use this phrase because it is catchy. Scientists usually use gentler language. Tension, anomaly, low probability, unusual coherence, extreme object, outlier candidate. These phrases lack cinematic thunder, but contain more truth. The Boss Great Wall may be large enough to provoke discussion, while still lying within plausible expectations depending on how measured. That is less dramatic than rebellion against physics. It is also more interesting. Because the universe need not break rules to surprise us. Now imagine two ways of understanding the same discovery. Version 1. This structure should not exist. Version 2. This structure helps refine the probability distribution of a large-scale clustering under current cosmological models. One sounds better in a trailer. The other builds actual knowledge. Now there is something calming in the role of simulations. They remind us that uncertainty can be explored systematically. We do not need to choose between blind confidence and cosmic panic. We can test scenarios, compare outputs, improve models, and learn gradually. That approach scales beyond astronomy. When life presents something that feels impossible, it may simply be outside your previous sample size. More data can be soothing. Now, another subtle point. Some simulations show that the universe naturally produces networks whose boundaries are fuzzy and whose connectivity depends on perspective. Giant walls may not be single monolithic things, but extended complexes of linked structures. That sounds familiar because it mirrors reality. Many large human systems are like this too. Cities blend into regions. Languages blend into dialect continua. Ecosystems blend into neighbouring ecosystems. Sharp labels are often conveniences imposed on gradients. The cosmos appears no less nuanced. Now, perhaps, the deepest lesson is this. If giant structures emerge from tiny early fluctuations under simple laws repeated over time, then enormity need not require special causes. Small beginnings plus persistence can create astonishing outcomes. Gravity knows this well. If the universe can generate walls so vast they challenge language, what does that say about our own need to measure meaning by size at all? Somewhere above you right now, whether clouds hide it or not, the universe continues without hurry. Galaxies turn through darkness. Stars burn with patient steadiness. Light crosses distances so large that language grows tired describing them. Clusters drift. Filaments hold their long invisible shapes. Structures like the Boss Great Wall remain where we have mapped them, vast beyond instinct, unconcerned with schedules, deadlines, headlines, or the small dramatic weather systems of human stress. And here you are, in one room on one world, during one evening of one brief life, listening to a story about scales too large to feel. There is something beautiful in that meeting. Tonight we followed a path from the familiar to the immense. We began with a name that sounded almost impossible, the Boss Great Wall. A wall not made of stone but of galaxies. Not solid, but patterned. Not built by intention, but grown through gravity over billions of years. We considered how astronomers found it, not by stepping outside the cosmos for a better view, but by collecting ancient light, measuring redshift, mapping positions, and letting structure emerge from patience. We watched galaxies become dots. We watched dots become patterns. We watched patterns become a web. We saw that the universe is not a random scattering of islands, but a textured place where matter gathers into filaments, nodes, walls, and enormous quiet voids. We learned that even these giant structures are not simple certainties. Their boundaries blur, their definitions depend on methods. Their significance depends on statistics, simulations, and better maps still to come. That uncertainty is not weakness, it is honesty. And honesty can be restful. Because the world often pressures us to appear certain about everything. Opinions arrive instantly, judgments harden quickly, answers are expected before questions have properly sat down. The universe asks for slower manners. It says, measure carefully. It says, compare evidence. It says, some truths take time. It says, even billion light-year questions may remain partly open for a while. There is comfort in that. We also spent time with scale, and scale can be medicine when handled gently. Many worries grow large because they are close. A message unanswered, a mistake replayed, a tomorrow not yet solved. Up close, these can fill the frame completely. Then astronomy opens a window, not to dismiss your life, never that, but to rebalance it. There exists a universe where light travels for billions of years, where galaxies gather into walls, where invisible matter shapes visible worlds, where our sun is one ordinary star among countless others. Within that perspective, some burdens shrink enough to breathe around. That does not make your concerns unreal. It makes them proportioned. And proportion is often kinder than panic. Now, there is a common misunderstanding that cosmic vastness should make us feel insignificant. I have never found that convincing. If anything, awareness makes us remarkable. A structure like the Boss Great Wall is enormous, yes, but it does not know it is enormous. It does not wonder. It does not ask questions. It does not sit quietly in the night trying to understand itself. You do. Consciousness may occupy a small physical volume, yet it opens a vast interior space. Through thought, mathematics, imagination, and shared language, a human mind can hold stars, walls, time, gravity, and mystery all in one gentle hour before sleep. That is not insignificance. That is a rare kind of grandeur. There is another comfort hidden in the cosmic web. Nothing truly stands alone. Galaxies belong to clusters. Clusters belong to larger patterns. Matter traces invisible frameworks. Local things participate in wider systems. Human life often works similarly. You belong to histories you did not begin, relationships you helped shape, places that shaped you back, languages built by countless strangers, knowledge carried across generations, kindness received and passed onward. Connection is not only astronomical, it is ordinary, and perhaps the ordinary forms matter most. Now think again about the phrase, too big to make sense. We used it because the Boss Great Wall strains intuition. But maybe the deeper lesson is that sense does not always come from shrinking things, until they feel manageable. Sometimes sense comes from accepting that reality exceeds instinct. You do not need to emotionally picture a billion light years for it to be true. You do not need to fully understand every layer of existence for your place within it to be real. You do not need complete certainty to rest. That last point is worth keeping close. Many people postpone peace until they have solved everything. The universe suggests another path. Stars burn amid unanswered questions. Galaxies turn amid incomplete maps. Scientists continue amid uncertainty. You too may rest before everything is resolved. Now the room around you returns. Perhaps the pillow has become heavier in the pleasant way. Perhaps the day has loosened slightly. Perhaps thoughts that arrived sharp are now softer at the edges. Outside, Earth continues its quiet rotation beneath the sky. The sun waits below some horizon. The Milky Way moves through space. Far beyond sight, the great walls and filaments remain part of the same reality that includes your breathing right now. That union of scales is gentle to remember. The vast does not cancel the small does not diminish the vast, they coexist. One final thought before we let the night continue. You're not required to carry the whole universe in your mind. It is enough to know that it is there, larger than worry, older than hurry, and spacious enough to contain both mystery and one tired human being settling into rest. Thank you for spending this time here with me. If you enjoyed this slow journey through the cosmos, you know what to do with liking, subscribing, and returning again whenever you'd like another quiet place to think. Until then, let the walls of galaxies keep their distances. Let gravity handle its long projects. Let unanswered questions remain patient. And let yourself drift, small and real and wonderfully present, through one calm corner of an immeasurable universe.